Hi, welcome. It's Monday. It's more than a week later, but I'm back. Hello. We're doing this again. Going to be doing some streaming this evening. As before, I'm continuing to try to write a WebAssembly interpreter in Ruby. That's what we're doing here. Um, Remind myself I'm doing this so I can have fun. I'm doing it to demystify WebAssembly for myself, maybe for you, and to share how I actually go about doing this. I want to have fun more than I'm concerned about making something that's particularly functional. I'm more interested in making something correct than making something that's fast. I want the code to be clear rather than clever. I want to write pure Ruby, try and avoid writing any C extensions if I can possibly avoid it. And I want to try and avoid adding any third-party dependencies as well. So that's what we're doing. I've had a week off, went on holiday. That was very nice. I have sort of forgotten everything that I was doing, which is a little bit of a worry. But, it'll be fun to get back into it with you live. So a brief retro, as always. I got floats float literals mostly working last time. So the 32-bit floats, I think the float literals were working entirely, which was good. I nearly got the 64-bit floats working, but I sort of ran out of, it was sort of after midnight and I sort of ran out of steam. So I didn't quite get those working. But overall it's good. I wasn't sure how painful this was going to be. So I'm relieved it's been mostly okay so far. That's, something worth celebrating. Of course, actually implementing the various arithmetic operations on floats could yet be the death of me. But we'll cross that bridge when we come to it. Also, in the last stream, once again, I piled quite a lot of code in, and it started to make a little bit of a mess again. I went back and just sort of read the code earlier today to remind myself of what I'd done. And yeah, it could probably use some cleanup. I think we'll find out now, but I think I'm a few tests away from having the 64-bit flows working. And then maybe once everything is working, that would be a good time to sort of do another round of cleanup and sort of get things looking a little bit tidier. I also wanted to talk briefly about audience participation. Hi, Chris. I'm very glad to see you here. I'm glad you're streaming from a train, so welcome, Zeta. And yeah, I suppose this is what I wanted to talk about. That people who've been showing up and have been in the chat have been really kind and encouraging, which I appreciate a lot. I wanted to call out a couple of specific contributions, one of which is this comment from Chris last time, this idea about encapsulating flow into a class. I've added this to my to-do list. I think this is a great idea. It's not clear to me when the right time to do this is. I'm a little bit nervous about sort of introducing structure too soon in case it turns out to sort of ossify something that's not actually right. But again, maybe once the tests are passing, that would be a good time for me to kind of introduce a float class and try and clean things up a bit. Chris also got in touch with me after the last stream with an interesting observation about the packing of floats, which I will get to shortly when we actually begin. But continuing on the theme of audience participation, Afuk very kindly submitted this pull request about, it says general spec compliance for floats. I have made an effort to not look directly at this PI yet, because I'm trying to let the tests guide my implementation, and I don't want this to unduly influence me. However, once I've got all of the float tests passing, I'm going to come back and see exactly what it is he's suggesting here. I mean, my hope would be that the tests we're using provoke enough of, whatever spec compliance means. I would hope that the tests are going to actually demand a degree of compliance with the spec, but we'll see. But that was very exciting. First pull request, thanks to Fook. And yeah, I suppose just generally, thank you very much to those people, and you, the person watching now, for participating and contributing. It's really rewarding that people are kind of joining in and taking an interest, and I appreciate your attention a lot. And I'm having fun so far, which was the main point of this, after all. So I think that's probably it, and I can just get stuck in and actually do some stuff. Like I said, I kind of added. I need to prune this to-do list. It's getting a bit long now. But yeah, some of this is stuff that I added last time, and then I've sort of come back and added stuff like the pull request from a Fook. Some of the stuff that Zeta pointed out, and then some other just like bits and pieces of like, I could potentially clean. A Fook also suggested, or I suppose sort of politely asked me, why I hadn't used string scanner in the S expression parser. That's a good question, to which I don't have a very good answer. The answer I gave to him was that I didn't really need it, because the S expression parser was so simple. I never really felt like I needed any help from the standard library, but I think probably using string scanner would be slightly nicer. So again, that's something I could go back and clean up in a little bit. And yeah, a few other just sort of miscellaneous cleanup things here. Anyway, I think the first order of business for me is to just sort of get my head back into where I was. I can't really remember where I was. How do I even run this? I'm really hoping that this is, yeah. Look, fortunately, I've got this in my history. Okay, yeah. So I was working my way through the float literals tests, and all of the. In fact, why don't I open a browser? WebAssembly spec, yeah. So I was looking at float literals. So at this point, just to state what's hopefully fairly obvious, I'm not even at all trying to implement any of the operations on these things. I'm just trying to implement the ability to correctly parse all of these 32-bit and 64-bit floating point numbers. So supporting all the various syntaxes. So this, this hexadecimal notation from what I think of this as the C99 hexadecimal float notation, and making sure that my interpretation of all of these floating point numbers lines up with what the spec is expecting. And I had a few problems with this, but got it working for 32-bit floats. A bunch of them are working for 64-bit floats, but we've got all the way down to F64 min positive. How far through the 64-bit ones is that? I mean, there's a load of other ones down here, but I would say this is like more than halfway through the 64-bit floats. So fingers crossed that we'll get to the end of it today. I'm just trying to think. Yeah, I think I'm going to get stuck straight back into this, actually. I was tempted to faff about with writing a script to run the tests. But that might be like a little treat for if I manage to get, because, if I can get all of floatliterals.wast working, then I'll want to add that to this file. Why did I do that? So yeah, I'll want to add another one in here, and maybe that would be a nice time to actually, it'll only be a few minutes to just stick all of this in a shell script and run the shell script from this GitHub Action workflow rather than have to keep adding them in here, and I can't actually run these from my local shell in any convenient way. So yeah, I'll save that up and do that afterwards. Ditto the Ruby version thing. That was just, again, that can be a little treat if I manage to get these tests passing. So, right. I'm just sort of waiting for my brain to remember what the problem was here. f64.minPositive. So this is... We'll go and have a look at the definition of this function in a sec. It'll be further up in this file. But you can see what it's expecting to get back is literally the integer 1. So this is expecting to get a 64-bit integer back where only the final bit is set. So all of my previous illustrations of floating point numbers here were only 32 bits long. But so that's 8, 6, 16, 32. So we're looking for this 64-bit floating point number. I can't remember how much I said about 64-bit. Oh yeah, I said a little bit. But of these 64 bits, as before, the first bit is the sign bit, and then you've got 11 bits of exponents. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then all of the rest of this is the fraction. I sort of alluded to this before, but I didn't really talk about it. That when all of the exponent is set to 0 here, this is a special case for IEEE 754 floating point numbers, which is that I mentioned before that normally the interpretation of this fraction is that the significand, so the thing that is being multiplied by 2 to the power of the exponent, is actually 1 point whatever this fraction is. So ordinarily, if you saw this as the fraction, ordinarily the interpretation of the significand would be 1 point this whole fraction. But when the exponent is all zeros like this is a special case called a subnormal number. Or rather, when they're all zeros like this, if the fraction is all zeros, then that is literally the number 0. If the fraction is non-zero, then the interpretation of this fraction here is that the significand is 0 point whatever this is, rather than 1 point. So this is a subnormal number. So it's just, in this case, it's just a very small number. And clearly what this represents is the smallest expressible number. This is actually, because of the way exponents are represented in IEEE 754, this is not 2 to the power of 0. This is 2 to the power of, I can't do the maths in my head, but essentially 2 to the power of minus, is it this? Because I don't want to get distracted by this, but anyway, it's 2 to the power of a large negative number multiplied by this binary fraction, which is already a very small number before you've even multiplied it by 2 to the power of minus something large. The point I'm making here is that this is a very small number. It's the smallest expressible number, which I guess is why this is called, oh yeah, when I say smallest, I mean the smallest magnitude positive number. Obviously, all of the negative numbers are lower than this, but this is the smallest magnitude positive number, and then the smallest magnitude negative number would just be the same thing with a 1 in the sign bit. So the thing being tested here is, can we correctly interpret the smallest possible positive 64-bit number? Now, there was an F32 min positive, I remember, and this is doing a similar kind of thing here. So wherever this was, min positive. Okay, yeah, so this was essentially the fraction is 1, and then it's times 2 to the power of minus 149. For F64, it is, oh yeah, this was the maths that I failed to do in my head. It's this binary. I was like, why is this so short? Because this is hexadecimal. I was like, that's nowhere near enough zeros. Each of these is a hexadecimal 0, so each one of these counts for 4 bits. So this has 4 times fewer zeros than appear there, which looks, I think what I'm saying is correct. So yes, so this is what I was expecting to see. So this is like the whole fraction is 0, and it's times 2 to the power of minus 1022. So that all makes sense, but what I don't know is why it's not working. We were expecting to get 1, but we got 0 here. So that means that somehow during the conversion, let's look at the code. So the way this works is, why does this happen? It was in the interpret float function, I think, yes. So what's going on is that we're in, well, specifically this case, I guess. So we're matching out the parts of this number. So we're matching out the leading 0 here, which is P, the trailing loads of zeros and then 1, which is Q, and then E, the exponent, is minus 1022. So we're pulling all those pieces out. And then we're doing this thing where we're sort of constructing a float by just doing the necessary arithmetic. So we're saying we'll take the whole part of this whole thing here is called the significand. So we're sort of taking the whole part of the significand, which is the 0, and then we're adding on the fractional part of the significand, which is all of those zeros and then a 1. And this 16 to the power of minus q dot length is to correct for the fact that it is after a decimal point. So we're sort of making it way smaller to account for the fact that it's all after the decimal point. And then multiplied by 2 times e to the power of, 2 times 2 to the power of e, which is this minus 1022. So this bit of arithmetic here, the intention is that this makes us this smallest expressible 64-bit float, and then we're just packing it into a string. So clearly something here is not working right. So let's have a look at that, because I can just reproduce this. So I know what P, Q, and E are actually. At this point, they're strings. So P is the 0. Q is all of the zeros with the 1. And E is minus 1022, I believe. And this line of code was saying, oh, it's just mapping to string, but those already are all strings. We were doing that in case any of these are all pieces from a regular expression match, and they could be nils. So that's forcing them to be strings. And then this is the thing that's actually computing the value. So I can just go ahead and try that. So value equals. Okay, so I guess that's sort of what I expected. So the numerator is 1. The denominator, is a very large number. So in principle, this should be the same number as this. But I guess what we're being told here is that if I pack this, what was the right format here? I think it was D for double. Oh, well, let's just have a look at it when it's packed. Yeah, these are all zeros. And what we were looking for was, I think this is big endian. No, I can't remember. I can't remember what the endian this is. This was something that was definitely swapped into my brain previously, but has now fallen out. But we were looking for one of these bytes to be a 1, whether the least significant one comes at the beginning or the end. And the point is that when we unpack this as a 64-bit integer, we were expecting to get the number 1 there, and instead we're getting the number 0. So we can see that that's not working quite right. Now, the thing that Zeta mentioned to me is that he had a look at this and he noticed that when this is clearly here value is a rational number, and when it's getting passed into pack here, it is in some way getting coerced into a float. But what Zeta noticed is that if you actually explicitly call to float on it, then you get the right answer. So that's a bit weird. I haven't had a chance to look into why this is. And I don't think it's going to be particularly easy to understand why this is. Let's have a look in pack.rb. This would be a great time if anyone is watching this on the stream to explain why this is happening. So where does this... Oh, there's just a primitive... Okay, so I'm gonna have to look in pack.c, perhaps not very surprisingly. So when you're packing a D, so yeah, this sort of quickly gets into, well, what it quickly does is get beyond stuff that I feel confident with. So this is getting into the C implementation. It does call RB to float on whatever value you've passed in here. And then there's this rfloat value macro that does something to it. But I feel like I'm trying to decide whether to investigate that. I don't really want to investigate that. I mean, this was a useful observation from Chris that that for some reason the implicit coercion here is doing something different than if we explicitly coerce it, which is very odd. But of course, what really matters is that this gives the right answer. So I'm just going to try doing that. Going to try coercing these to float. So both of these produce rationals, and previously the assumption was that just providing the raw rational here and allowing pack to coerce it to the right kind of float was going to work fine, but somehow something is going wrong there that I don't really understand. Yeah, I think I'm going to resist the temptation to investigate that for the moment. I know that's a little bit incurious of me, but mainly I just want to get to a point where this is working. And then if it's sufficiently interesting, we can investigate. So I'm going to say, understand why explicit coercion with 2f, of a rational produces different pack results than allowing implicit coercion. I'm not sure whether I'm going to actually do that, but I mean, I'm definitely interested. Whether I'll investigate it on the stream or if I'll just ask someone who knows more about the Ruby internals than I do. I don't know, it's sort of tempting to ask someone who knows what they're doing to investigate that. Anyway, so I suppose this is sort of a workaround So let's see how far that gets us. Well, it gets us a bit further. Because now this is returning the right answer as expected. And now also this min normal is also passing. Right. So this min normal is yes. Okay. So whereas previously, let's see what the expectation is there. F64 min normal. Yeah. So whereas this number here is the smallest subnormal number, I believe that the smallest normal number is the one where the exponent is non-zero. So this is the smallest possible exponent. And then I think all of the rest of it should be zeros. So I think this is the number that we're talking about. It's positive. It's got a non-zero exponent, but all of the fraction bits are zeros, which again, of course, means that the significand here is 1 dot all zeros. So I think this makes sense. So this is saying that there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sets of 4 here. Yeah, that works. Okay. And then there's just a single one. And there is the single one. So this is what I was expecting. Anyway, so the point, I suppose, is that that's... In fact, I misread these results because it has actually blasted through. Sorry, I missed the fact that we've actually done all of the F64 ones here. We've got into these F64 underscore deck. So what's the difference with these? Is it that they're decimal notation rather than hex notation? Yes. Okay. So actually all of these worked. And so now we're down to here. And is it which one's failed? Max subnormal. Okay. So this is... So again, what's the largest subnormal 64-bit float? I would expect that to be all ones here. So instead of being, what is this, 52, 53? Well, there are 64. There's 11 there, and there's 1 there. So we've got 12 bits. So there should be 52 bits left here. So there should be 52 ones here. So that's the number we're expecting to see. Max subnormal, yeah. And that looks pretty much like this. Like that's what I would expect to see in hexadecimal notation, you know, the smallest possible exponent. And then this FFFFFFF to indicate these 52 ones. So why is it not working in decimal notation? Let's investigate that again. So I can do this PQE thing again. This time P is going to be 2 and Q is going to be this huge number and E is going to be minus 308. Okay, and then to assemble the value, it's almost the same as before, but we need to, these radixes need to change. So it's, instead of 16, it's 10. And instead of 2, it's also 10. So in fact, all of the radixes here are 10s. So this is because the significand is written in base 10. That's why those are all 10s. And then actually, sort of separately, it's times 10 to the power of whatever the exponent is. So in decimal notation, all of the radix of the significand and the base of the exponent is always 10. So, so we've got that huge number over that huge number. If I just convert that to a float, so we do get, you know, this looks like a convincing float, but what do we get when we pack it? So these are all zeros. That's very strange. When it's converted to a float first, we get something different again, which I think is not right. Well, I know is not right because the test's failing. So what actually is this? I mean, that looks right, doesn't it? Oh, it's oh, God. I was doing the wrong thing. I was doing the wrong... okay. It's max subnormal. Not min normal. It's because my search had highlighted the min normal. I was doing the wrong thing there. Right, okay, that was a waste of time. Apologies. So... yeah, unsurprisingly, this is a very close... so the largest subnormal number is really very close to the smallest normal number. These are just either side. These are sort of consecutive floating point numbers just either side of that boundary, where the normal numbers with the non-zero exponent, or the non-zero bits in the exponent, tip over into the subnormal numbers with all 0 bits in the exponent. So yeah, it's very close, but it's not the same. So have I got the right one? Yes. Okay, so that's the number we actually want. Again, I mean, that looks superficially fine. Oh, that's the same. Okay. Yeah, so I don't know what's happening here. I assume it's some kind of rounding behavior. And I don't know if I've got any control over that. I suppose what I'm really wondering about is when rational gets converted to a float. Returns the value as a float. So previously we were getting this 72014. This is coming out as the same number, 72014. So yeah, these two numbers that are extremely close to each other. So the previous one was this, ends in 2012. Is supposed to come out as a different number than the one that ends in 2011. but it's coming out as the same number. And then, yeah, unsurprisingly, when we pack this, we're going to get exactly the same thing as we got for the other one. So this is supposed to be all F's here and a sort of an implicit 0 at the top here, but instead it's sort of rounded up to have a 1 in the leading position there. So I'm not entirely sure what to do about this. Although there is this here, now that I'm looking at this, there's this thing that converts it to a big decimal. What would that look like? Because this was one of the things that Zeta suggested last time. Try big decimal to address, well, in this case, smallest possible double precision float woes. So this was the woe that ultimately got addressed by doing that coercion by calling to F explicitly rather than allowing it to happen implicitly. But we've just got a different flavor of problem here. So what happens if I call to D on this? Undefined method to D. Do I need to require big decimal? Maybe this documentation is just a lie. Oh, require big decimal util, it says. And I have to give a precision. What significant digits for the result? I don't know how many significant digits I want. A large number. I mean, it's not that large. But like, I'll have it as like 20. Okay. So does that make any difference? Like if I pack this, so if instead of calling to F here, I call to D20. Yes, that gives the right answer. But so that's good. I still don't really understand what's going on here, but something in the so because that rational value, this thing, is absolutely precise. Like this is just a ratio between two integers, so there's been no loss of precision here, and Ruby has arbitrary precision integers, so these will just keep getting larger and larger forever. So this is precisely the correct number, but somehow whatever is going on inside the guts of value to F is rounding off this, is rounding off the significand in a way that disagrees with what WebAssembly wants to happen. And then for whatever reason, converting it to a big decimal first prevents that from happening, and we get the right answer here. And I assume that if I go back to the 2012 value, i.e. the smallest normal number rather than the largest subnormal number, if I pack this, yeah. So again, I'm sort of at the limit of my understanding of how much control we have over this aspect of Ruby's implementation. Like, I don't know, because IEEE 754 has got all kinds of, has got like different rounding modes and stuff. Like this is in a full-blown implementation of IEEE floats, you can control this kind of behavior, but I don't know if Ruby lets you do that. Yeah, I'm a little bit out of my depth here. I've never really messed with this. I can't. I was hoping I might see something in here that gave a degree of control over this, but I can't. I can't see anything in here that I can't see anything that you can configure to control how this works. So I think, just reading this. No, that doesn't really seem to be. I may well be missing something here, but I can't see anything here that lets me control like the rounding mode when a rational number is converted into a flow. I didn't see anything in either this rational documentation or in the float documentation that see, there's this round. What's this? Returns rational number rounded to the nearest value with the precision of the n digits, number of digits, default 0. Returns a rational when n digits is positive. So this doesn't actually produce a float. This just produces another, like, this reduces the precision of the rational number. So that's not what I want. I was a little bit, this thing here, half, is suggestive that you might be able to control. Oh yeah, so this is what float round does. Right, so again, this is, if you've already got a float, this allows you to round it in a particular way, and this is what do you do if you're rounding, what do you do if you're at 0.5 essentially. You can round away from 0, round towards 0, or you can, and I believe this is what WebAssembly does, is round towards even. Anyway, I don't think this is getting me anywhere. This might be too defeatist, but I am tempted to believe / guess that there's no straightforward way for me to force the conversion of a rational directly into a float, and that my best bet is to go via a big decimal here. Now, the problem is I don't really like this. I don't like having to specify how many, because I don't know how many decimal points I want. I mean, I could just take a worst case. Like, I guess this is however many digits that is the worst case. But length is what I wanted. 16. So it seems like 16 decimal digits is probably the most I would need, but that feels very arbitrary to me, and I don't like it. I mean, even though 16 is a nice round number in base 2, that still feels a bit of like a coincidence more than anything. So what if this whole expression just produces a big decimal? I mean, really, the problematic places are these exponents, right? Like, this produces a very small number, potentially, depending on how long Q is, and this produces a very large number, potentially, depending on how big E is. Or it could be a very small number as well, if E is negative. And then those just get multiplied by and added to a couple of sort of normal ish sized integers. So what happens if I make this a big decimal? Can't omit precision for a rational. Is it supposed to be .new? I thought there was a helper that did this, but no. Can't omit precision for a rational. Oh, okay, because right. So the number that comes out of this is already a rational. This 10 to the power of minus q dot length. So what about if I just start with a big decimal here? Okay. Well, that's interesting. It's definitely produced a different looking number than this one. This one ended 72014. This one ends 72012. So what happens if I pack that now? I can't remember if this is the, I can't remember which one this is. Let me just start again. This is what we're trying to look at, max subnormal. So we're looking, this is not the right result for the max subnormal, but let's just make sure that because I know I was comparing the two earlier. So yeah, this should be 2011 for the max subnormal. So if I do this, so this is sort of, I mean, this is literally the exact same thing as I wrote here. It's just shifted one decimal place down. So if I pack that, right, so that looks okay. So what happens if I back out of this to, do I want to, I think I'm going to commit that to float thing, because that did achieve something. So let's say manually, or not manually, explicitly. Hi, Stephen. Yes, this is the train edition of this stream, apparently. I hope you also are on a train, or looking at a train, or perhaps just thinking about a train. Whatever makes you happy. Explicitly convert rational to float when packing, before packing. Well, that's very kind, Stephen. I'm glad that this ranks as almost as fun as being on a train, or looking at a train, or thinking about a train. That's a standard which I would never previously have hoped to reach. That was an excellent bit of audience participation there, so thank you for that. So the example, I just wanted to give the example that we were stuck on earlier. I should have written this at the time, because now I'm it was min positive that was the problem, wasn't it? For some reason, array.pack doesn't convert a rational to a float in the same way as doing it explicitly, i.e. by calling this was causing a problem when packing, which was being rounded down to 0. Test F64 min positive, which is being rounded down to 0. converting the float, converting the rational to a float before packing it makes the problem go away. I don't really understand why this is happening, but I'm not going to investigate at this stage. Thank you, Zeta, for spotting this weird behavior. Okay, so that is a thing that happened. Let's not pretend it didn't happen. But I think what I'm going to do now is remove that again and change. What do I want to do here? I think what I'm going to do, which might be overkill, because what I did here was that I changed this exponent to be a big decimal. Maybe, I mean, does it matter? I feel like at least one of these needs to be a big decimal in order to make the final result a big decimal. See, that's not as good, is it? That's wrong. That's right. Okay, so I'm gonna... I don't know. I feel like I'm being very intellectually incurious here because there's something weird happening with the precision of this expression. But I'm conscious of what I said in previous streams about the fact that this is really taking a lot longer than I was expecting it to. And so although I am, believe me, intellectually curious about exactly what's going on here, that is in tension with the desire to like get this working as quickly as possible. And I think that because it's these exponential expressions here that have the potential to yield a very precise number, a very small or a very large number, then I think if I belt and braces would be to make both of these big decimals, and then I can see here that gives the right answer in this case. So what I'm going to do is make this big decimal, make this big decimal, and then do the same. I need to, one of the refactorings I've got here is to extract this expression, extract the duplication of the float assembling code and interpret flows. So the fact that I haven't done that yet means I'm having to double up here, which is a bit annoying. My vimfoo is not really good enough to make this convenient. So that's sort of essentially undoing the zeta maneuver and replacing it with, and I'll need to require big decimal. And I don't think I need big decimal util because I think that's the thing that like monkey patch is rational and things like that. Whereas here I'm just calling this kernel method that creates big decimals. And I haven't really said anything about big decimals, so let me just show that briefly in the interest of showing my working. So yeah, big decimal provides arbitrary precision floating point decimal arithmetic. So that's, yeah, I should have said this sooner. Like, what big decimal is giving us here is, rather than the float class that is built into Ruby is just sort of locked to use IEEE 754 64-bit floating point numbers. That's the only precision that you can have, which gives me the willies a bit because we do need a 32-bit. We do need 32-bit numbers, and so far that hasn't been a problem. But I'm a bit nervous when we start doing arithmetic on them, like using 64-bit numbers to approximate 32-bit numbers. Obviously, 64-bit numbers are better than 32-bit numbers, but I'm sort of worried that artifacts of rounding that the spec, edge cases that the spec might be testing for might sort of not work out right with 64-bit numbers. But that's a separate problem. But the point is, any arithmetic that you're doing with floating point numbers is sort of locked into a 64-bit float. Big decimal gives exactly what it says, arbitrary precision floating point numbers. So here we go. Decimal arithmetic is useful for general calculation. It provides the correct answers people expect, whereas normal binary floating point arithmetic often introduces subtle errors because of the conversion between base 10 and base 2. So this just gives us a way to create and manipulate arbitrary precision floating point numbers. So, I don't want to get sucked into reading this, but I'm hoping that using this here and making the result here be a big decimal, which we saw did the right thing when we packed it as a float, it's clearly avoiding whatever rounding behavior was causing us problems before. I don't even know if it was a rounding error, but like whatever precision problem we were experiencing before seems to have gone away. So anyway, that's enough talk. I don't know why I'm delaying the gratification of running these tests. This should have been the first thing that I did. Oh, wow. That's great. We've made it all the way down to F64 decimal root beer float, which is this one. This was the amusing tweet that we investigated last time. And then it's failing on this, but this is failing for an extremely boring reason, which is that it's got underscores in it. And that's much more the category of problem that I am intellectually capable of solving, because I know how to remove underscores from a string in Ruby. So that's very exciting. We've basically got all of the what I consider to be difficult tests passing there. So let's celebrate by making a commit here. And I'm going to say something like use big decimal instead of rational to represent float significand and exponent. So where was I want to write this in the commit message where our problem was. Goodness. So the one that was causing a problem was this one, F64 max subnormal. So the previous approach worked for almost all the tests, but failed on F64 max subnormal. By using a big decimal instead of a rational when assembling the float, we avoid the mysterious loss of precision that was causing this value to get rounded up to the smallest normal number. Again, I don't really understand what's going on here, but I'm choosing to prioritize making progress over fully understanding the problem. That's engineering. So okay, well now, like I said, this seems like a kind of problem I can actually solve. So the problem is that the string that's coming in at the top here, so we're already doing some cleanup on it. We're doing delete plus and delete minus from the as prefixes. So let's just say also get rid of underscores. Okay, so the decimal separator thing worked. So let's say remove underscores, or remove underscores from floating point literals during parsing. There's not much more to say than that. I think that is self-explanatory. Now I saw that failure there was to do with case sensitivity, because this is saying oh yeah, we don't get a test name here, but I mean, this, I don't think it's intentionally, or at least it's not explicitly mentioning that it's testing this, but I can just see that this has got a capital E in the middle of it. So that's why that's failing to parse, because these regular expressions here are looking specifically for a lowercase p and a lowercase e, which is a bit of an oversight on my part. So I might as well make both of these case insensitive. What about this one? Nan. Is that supposed to be? Let's just have a look at the spec. So text format. Lexical format. And no, that's not useful. Okay, values. Flipping math jacks. See, it's interesting, isn't it, that, or at least I think it's interesting, that this 0x to represent a hex number, and the 0x inside a nan is explicitly not case insensitive. Like, I don't think this really matters, but it is curious that, I mean, maybe I should be a little bit more disciplined. Like I said, part of the purpose of this project is to try and be, I am trying to be correct. And I was sort of expecting to see something here that was just hand waving and saying, oh, this is all case insensitive. But actually looking at this, I can see that they're explicitly calling out that it can be an upper or a lowercase e and an upper or a lowercase p. But that does not extend to things like nan or the 0x that precedes a hex number of any kind. So I think I'm actually going to recreate that pedantry here and say that this can be little or big P and this can be little or big E. I mean, that does now make me a little bit nervous about the fact that for the hexadecimal one, that doesn't consider the possibility of uppercase hex digits, which I'm sure this is going to. Yeah, so this does, again, explicitly allow upper and lowercase hex digits. Is that going to be tested here? These are all decimal. Yeah, so we're going to see a failure extremely soon, because there's a capital A here, which I think is the first time we've seen a capital digit in a hex number. But I believe the specific problem we're seeing here is this exponent separator needs to be case insensitive. So rather than just get very excited and make this whole regular expression case insensitive, I'm going to do the pedantic thing of making just the exponent separator, case insensitive. It's funny that here they do big E and then little e. Let's do that. I suppose that's the order they go in ASCII as well. Okay, so what I'm looking for now is for us to get further than, well, I want to see F32 decimal separator 5 pass. Yeah, okay. That did pass. So this is make, I mean, I suppose I didn't need to do this for, I would have needed to do it down here. So I'm not, even though I've sort of speculatively done it for both of them, I am actually going to need it. Make exponent separator characters case insensitive. And then I'm going to, I think I'm going to link to this part of the spec actually. The WebAssembly spec says that the separator characters in a floating point literal, E for decimal floats, P for hex floats, can be lower or uppercase. I guess this is the I've changed this explicitly. Yeah. I've relaxed these characters specifically in the appropriate regular expressions rather than making the entire regular expression case insensitive, because other characters, e.g. the 0x prefix for hex literals, are not case insensitive according to the spec. This doesn't really matter, but I'm being pedantic. Right. So, but then it failed for the reason that it was expecting this to be lowercase, but it's not. So I need to make these case insensitives. Now, again, I can just straightforwardly do this. I mean, maybe that is what I'll do. It was making me think of where even is this in the documentation? It's in regex, I suppose. It was making me think of what are they, character classes? Oh yeah, POSIX bracket expressions, because that expression I've just written, 0 to 9, lowercase a to f, uppercase a to f, is actually this x digit POSIX bracket expression. Well, let's see if this, I think there's two separate things here, right? Like, oh yeah, this should also, yeah, sort of anywhere that you can have a hex digit, it should be allowing uppercase A to F. But maybe there's a separate commit here, which is like, stop writing these out longhand when there's a POSIX bracket expression that means the same thing. Right, so those all worked. I think that's it. I think that's all of them. I mean, I know there's a failure here, but I think that's all of these. That's all of the tests that I was expecting to be able to run, and then the only problem is this binary does not respond to deconstruct module binary. Right, okay. Yeah, so it's when we try to evaluate this that it's not working. Okay, so hold on. This did actually work. So I'm going to say allow uppercase letters in hex literals. I mean, again, do I need to justify that? Yeah, I'm going to say per the previous commit, I'm doing this explicitly rather than making the because not all characters, not all parts of the floating point literal syntax are case insensitive. I'll give another example, e.g. nan inf. So I think, I mean, this isn't strictly necessary, but since I'm in here, I think I'm going to do this because it immediately, the fact that I was having to massage this to include all allowed hex digits is an indication that I'm doing something a bit silly. So I think I should use X digit here. So, oh goodness. How does Vim work? That's okay. I'm worried about meta characters here. But let's see what happens. If I swap 0 to 9, A to F, A to F, closing square bracket for this everywhere, well, I was right to be worried because that's absolutely not what I meant. What a disaster that was. Do I need to escape these? Yes. Okay. So now, does this still work? Yes, that is the same error as before. While I'm in here, do I have these anywhere else? Because I can see I know I've got 0 to 9s in here, which I could just use \d for, and I think I have in other places, but the reason I didn't do that here is because it's sort of for regularity with the places where I was including A to F. But now that I'm using X digit there, I should probably use digit here again for sort of regularity. I just wonder if I'm using it anywhere else. Let's find out. So if this is just 0 to 9, then this is just digit. So let's just check everything's working. Yeah, that's fine. I can get rid of this tab actually. So that's the nan payload. These are the significand and the exponent. Yeah, okay, so that is actually the only place that I was... Do I have a \d somewhere else? Oh, yeah. That's a bit of a distraction. Say digit. instead of \d in, what is it, slice expressions. I'm not sure that that's worth messing with right now. I was intending to operate on these regular expressions, and that is what I've done. Sort of wonder if these would be clearer if they weren't so exploded. Like the indentation isn't really it isn't very illuminating now that I've got these expressions here, but that's improve indentation of float regex, maybe. Oh wow, I didn't realize I had changed that. Oh, it's because I pressed Control A because I thought I was inside GNU screen, which I am not. Yeah, muscle memory is a strange thing. Okay, so these are called, I knew I shouldn't have closed that tab. POSIX, yeah, okay. Use POSIX bracket expressions for decimal and hex digits in float literals. So I think I'm just going to say this makes it clearer what it is we're trying to match, and means we don't need to worry about case sensitivity because these bracket expressions already match exactly the correct set of characters. Don't need to worry about getting the case sensitivity right, basically. I know we had already got it right, but I think this just makes it a lot clearer that we're delegating that responsibility to POSIX. Like it's not our problem, it's somebody else's problem. So let me just I just want to take one last look at these regular expressions to make sure that there's no other low-hanging fruit here. In fact, while I'm in here, there is this, I wasn't going to do this until later, but actually, given that I'm here, when I was reading through this code, if this code had been given to me for code review, I would have complained about this, because I know that you don't need to do this question mark, this question mark colon thing, which means it provides grouping without capturing. You don't need to do that if you've got named captures, because if you've got named captures, then the unnamed captures don't do anything. In fact, can I substantiate that? If a named capture is used in a regular expression, then parentheses used for grouping, which would otherwise result in an unnamed capture, are treated as non-capturing. So that is a long-winded way of saying when you've got a named capture group, you don't need to worry about having, you can see here that this second set of parentheses here does not capture the B, because these parentheses do not make a capture group in a regular expression that's got a named capture group in it. So while I am in here, I'm going to actually do this because this annoyed me when I noticed it. It's not a huge deal, but it's syntactic noise, and it's not doing anything useful. And really, regular expressions are already cryptic enough without having syntax in them that is not doing anything. So while I'm in here doing this regular expression surgery, I might as well tweak these to be, minimal. I think that's everything though. Yeah, I can't see anything else in here. I can't see any other opportunities like this sort of, obviously the E and the P, that's not a POSIX. There's no equivalent POSIX expression, and I don't think there's a POSIX expression for the... I don't think there's a POSIX bracket expression for plus and minus characters. So yeah, I think I'm just going to leave that. I'm going to leave that as it is. Let's just check that it's still this. Yeah, that shouldn't have changed anything. Okay. So what does it call it? Remove unnecessary. Well, I guess I'll just say remove unnecessary. I'm just gonna copy this because I've already written it. Oh, silly Apple Notes. I'm gonna say these don't do anything in a regular expression with named groups because parentheses don't capture in that case. Parentheses already don't capture in that case. Okay, tick. Like I said, I wasn't going to do that, but I happened to end up in that region anyway, so why not? Okay, so we're dangerously close to being done with the 64-bit, or with all of the float literals. The only thing outstanding is this. So I believe what's happening there is that when we hit... So it's saying binary does not respond to deconstruct. I think it's because this module binary here is, at the moment we have module. This is the only syntax we've seen so far. Module followed by an array of function definitions. And so here we say module splat expressions, and then we try to iterate over them. But here it's trying to splat this string binary. Is that right? What's going on? Or maybe it's here. Oh yeah, sorry. It's so this is fine. But then when we try to match, so this ends up being a single element array containing the string binary. And so we iterate over that once. This is the string binary, and then we try to match the string binary against this array, and that's where it's calling, that's where the pattern match is calling deconstruct on expression, which is binary in that case, the string binary. And that obviously doesn't work because that's not what we intended. So I think I'm just going to ignore this for now. So I'm going to say we're going to have a separate case here for module binary, and I'm just going to skip this. Like this is a whole separate problem of how do we... I don't have a parser for this. What I assume is the binary, this is sort of inline binary WebAssembly that needs to be interpreted as this function definition so that we can invoke it here. There's no way that I'm going to implement that right now, so I just want to skip it. So I think what I'm expecting to see now is not this error, because we should silently skip over that module definition, but now I'm expecting this assert to blow up because it's going to try to invoke this function and not succeed. Right, couldn't find function 429, blah, blah, blah. So right now it says raise couldn't find function. I think what I'm going to do is... I think I'm just going to turn this into a warning. I'm going to say if the function doesn't exist, then this is going to say... So instead of raising, it's just going to Could it be warn? Is that a thing? I mean, it is a thing. I didn't imagine that that was a thing. What does that look like? Does that actually emit anything? Because I don't know if... Yeah. So I might as well use that. What does that actually do? If warnings have been disabled, does nothing. Otherwise converts each of the messages to strings, right? So I think that's fine. I mean, I was just going to use puts, but, you know, warn is a nicer method to use here. So here I'm going to say couldn't find function, skipping, and then we're going to say next. Because what we just saw is that it plows on and does all the rest of this, which is not what we want. Whereas this next here is going to skip past the current command, which in this case is the assert, and then it's just going to carry on to this assert malformed here, which is what we want. I don't want to break here. I just want to go to the next iteration of the loop. Let's put in a thing here that says could be binary. Because that at least gives a little bit of... gives a bit of an excuse as to why we're just skipping it. I'm just wondering if there's any way of actually detecting this case, but I don't think there is. For me to even know that this is the name of the function being defined here, I would have to essentially decode this, and I don't know how. So I think I'm just gonna deal with the fact that we get a warning, but that's fine. And at the very least, we get a hint here that says it could be binary. I mean, that's a little bit cryptic, but I'll remember what that means, and that's all that matters. So let's say skip module binary and tolerate the resulting failure to find a function. We can't parse these binary modules at the moment. So the quickest solution is to just ignore them and not allow the missing functions to cause the test to fail. The warning should be of course, other mistakes might cause functions to be missing, but hopefully the warning is enough to alert the user to what's happening. You know, it's fine, is what I'm trying to say there. It's fine. Just don't worry about it. Great. Well, that's exciting. Hopefully these tests are all going to pass on GitHub and life will be good. Life is good. Fantastic. All right. So that was nice. And just thinking, what have I done here? I've done try big decimal. So again, that was basically Chris's idea. I could have a look at Fuchs PR now to see. I mean, we definitely found a couple of problems with spec compliance syntactically. So the case sensitivity and the underscores. So I'd be interested to see whether that is exactly what he predicted or if he has anticipated some other problem that hasn't been provoked yet. Tidy out the S expression parser. All the rest of this is just sort of faffing around with refactoring. I think what I'm going to do before I continue is do a little bit of these infrastructure chores, because otherwise I'll never get around to them. And I said that this could be my little treat for having made that test pass. So now, and in fact, I haven't, well, until they ran on GitHub, I hadn't checked to see whether all of the rest of them were still passing, which of course I was expecting them to. But, you know, it's nice to be able to actually check that. So I think what I'm going to do is, yeah, I'm going to, hopefully this will only take a minute. I'm going to make a little shell script. What's the right way to do this? How do you write a shell script? Can I just use that? And then what are my workflows? Basically, this is what I... Oh, well, before I do this... Yeah, I just realized that I didn't actually add float literals. There was me triumphantly pushing it and watching the tests pass. But I hadn't changed what tests run. So I think this is right? Oh, except of course it's a different... Yes, it needs to run from here. This is something I should think about with the test script I'm about to write, is try and make it not matter what directory it's run from. Okay, great. So yeah, before I forget to do that, let's say, what did I say here previously? Add float literals.wast to CI tests. Yes. This is all we really care about, of course. Not simply rerunning the tests that were already running, but running some new ones. It's going to take a little while. But anyway, I'm sure it passes. Yeah, there we go. So I don't know why I'm closing that, because we're probably going to go back to that quite soon. So test.sh, workflows. So the reason I opened this in the first place was just sort of yank all this out and stick it all in here. I mean, of course, it immediately occurs to me that if we're gonna write a shell script here, then I might as well say like for script in literals i32 i64 int exprs float literals, and then I can... How do shell scripts work? Something like that, right? So instead of listing all of these individually, I can just do it once. Sorry, my brain's taking this one laborious step at a time. So this bit here, I can just put script in. And then if I'm standing in the right directory, it will run all of those tests. So I assume if I'm in this directory, yeah, it doesn't work right. I mean, that's not a problem for running it on GitHub, but it is a bit of a problem for running it locally. This is part of the reason why I wanted this. Well, I'm going to take this a step at a time. Because I've got something that works here. So let's say add shell script to run tests. Let's say right now this needs to be run from the right directory, i.e. one containing the Wasmina and spec directories. Yeah, so there's a few things. I can see several things about this that I dislike, but I think the first thing I dislike is, well, I dislike the dependence. I don't like it that I can't run this from this directory, and I also don't like it that the directory that the WebAssembly tests are in is hard-coded there. Again, for the purposes of running this locally, I would really rather be able to point at that. I'm just going to amend this and say, these are copied from GitHub workflows ci.yaml with a for loop thrown in to reduce duplication. These test commands are copied from. So I think I can deal with that by using dir name. So when I run this script, if I get it to ask for its own dir name, then that is the directory that needs to be added to the load path, and in which this wasmina.rb script can be found. So if before I run this, I say, let's set environment variable wasmina path equals, and then if I in a subshell ask for dir name, and then that's the $0 is the name of the script, the file name of the script that's being run. And then I think in all these places, rather than saying, not all of them, but most of them, I want to say, I guess in quotes, like that. Does that make sense? Replace that one, replace that one, replace that one, replace that one. Don't replace that one. So I think now I can still run it from standing up there, but now I can at least try to run it from here. Then there's a different problem, which is that it now can't find that spec folder. So let's say dynamically, let's say, use scripts directory as wasmina path in test script. And then there's this separate problem. I think probably what I should do is have an environment variable that's pointing to this. So rather than hard coding this spec directory, I think I should have some other thing, wasm spec path. And then that just means that the person who's running this script is now responsible. Like if I don't, now I have to set wasm spec path is that, and then I can run this. Yeah, that's what I want. Use wasm spec path to find WebAssembly in test script. So now wherever I, here, if I say wasm spec path equals spec, wasmina test, that also works. Okay, that's what I wanted. What else is problematic here? Well, so in the workflow, each of these is run separately, and we're sort of relying on the fact that GitHub Actions will check the exit status of each of these commands to determine whether it's succeeded or not. Whereas now in this script, I think it's probably only the last one. Let's see, if I spec test core float literals, if I break one of these, let's say this one, let's put a 1 on the end. If I run this, so I'd expect the exit status there to be non-zero, indicating an error. But I sort of suspect, if I undo that, I sort of suspect that if I change, so if we look at spec test core int literals, if I break this one in a similar way, change that to a 6, and yeah, I fixed that one. Oh, did I think I forgot to save that. So the failure kind of scrolled past at the top there. Somewhere, I missed it. But I think probably, yeah, the exit status is 0, indicating success because the most recent one, the float literal, the final thing that executed, succeeded. So I think I'm going to have to do the set -e thing here to sort of turn on the, I know this isn't a perfect mechanism, but it'll give me what I want here. I said I would try and GNU.org/software. I know this is not bash that I'm using, but I think there's probably some documentation of this. the set built in. Here we go. Set -e, exit immediately if a pipeline, blah, 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 a list or a compound command returns a non-zero status. So essentially what I'm hoping this will do is cause this to stop at the point where there was a failure, which means that the exit status is now 1, because that's implicit in what I'm talking about here, is that the purpose of having this script is to be able to run it both locally and on GitHub Actions. And so it's important to me, not locally so much, but it's important to me that on GitHub Actions, it reports an error exit code if the tests aren't passing, because otherwise GitHub Actions is not going to know whether to give me a green tick or a red cross, which is, of course, the whole point of GitHub Actions. So, yes. So if I now unbreak this, there we go. And if I re-break it, okay. Sort of weird that there's no standard output in that case. But still, I think this is an improvement. Use set -e in test script to stop on error. Perhaps. Yeah, I mean the problem now is that I'm not getting all of that output. I guess I might be able to guess from the test name here, but previously I got quite a nice sense of how far it had got, and now that's kind of gone away. I wonder, because there's another one, I think it's X, that sort of is like a tracing option that shows you all the commands that are being run and probably all of the output. Print a trace of simple commands and their arguments and yeah. So I think that if I stick an X on the end here, then well, I'm still not seeing. Oh, is the reason I'm not seeing any output that this is literally the first one? But I didn't realize that before, but I think it is. I think it's because this is the very first. But like if I change this to 11. See, it wasn't until I had that tracing in that even occurred to me. But yes, okay. So, all right. So the reason I wasn't seeing standard out is because there wasn't any. That's not the shell's fault. But I think having this tracing on, like having that tracing on, made me realize what was going on. So I think that's good actually. So I'm going to, what did I say? Use set -x in test script to trace commands. This makes it easier to see how far we've got before a failure. Which is exactly what I wanted in that case. And I believe that's preserved. Let me just double check. Yeah. And then if I fix the tests. Yeah, I kind of like that. I like that this output is now broken up. I mean, this is very rudimentary, but I'm glad it's broken up by, if I'm digging through the result of GitHub Actions trying to figure out what's going on, just having this little demarcation showing me which test script is being run is better than nothing, I think. Yeah, now we've got 0, which means everything is fine. So that's all good. I suppose what the reason I was doing this was to integrate it into the GitHub action. So I'm going to split this. Because that lets me tick this off. I have written a script to run the tests, and now I've got a separate job to do. Sort of slightly, I don't know who I'm trying to fool here by gaming my own to-do list, but you know, it makes me feel good to check stuff off the list. So I need to go to my ci.yaml. So essentially I can replace all of these with, well, I need to be a little bit careful here, don't I? So what I'm thinking is, basically I can get rid of all of that and just run test.sh, right? But it's complicated slightly by the fact that I've got these two repos checked out. So it's actually wasminer / test.sh. And I need to set an environment variable to tell it where the WebAssembly spec path is. And right now that's hard-coded in here. So I'm thinking that maybe what I'll do is, what you can do in GitHub Actions is you can have an expression. In fact, context is the kind of expression I want. So you can write expressions that look like this. So here, what I don't want to do is just duplicate this magic string. Like sorry, I should be more articulate. What I don't want to do is just copy and paste this path here, and like set an environment variable down here to the same value. What I'd rather do is set that environment variable once, like up here, because in GitHub Actions you can say like, and this is contexts, you can provide this env context that you can populate with, here we go, workflow syntax. Where's env? Here. So this lets you, so I can do this. I can say wasm, what was it, spec path is spec. And then down here, instead of having, well, so firstly, that is sufficient to set the environment variable that this test is expecting to see, that this script is expecting to see. But then rather than have it duplicated like that, here I can use an expression that uses the env context to retrieve the value of that environment variable. So env dot whatever will give me the value of that environment variable. So, you know, this kind of thing. I don't think, you know, the temptation is to say, is to just do that. But I don't think that the value of this key is necessarily gonna, if this was gonna be interpolated by the shell, then that would be fine, but I'm not confident that it will be. Whereas this syntax, this expression syntax is kind of, this will get interpolated before whatever action, before this action / checkout v3 gets this value, it will be interpolated by GitHub Actions. So I think I can just say env.wasm spec path here. And that will, just to clarify what on earth I'm doing here. What I'm doing here is telling it to clone the WebAssembly spec repository into the directory whose path is whatever I have set the wasm spec path environment variable to be, which is where this script is going to look to try to figure out where to find those files. So I think that this will work. So what have I done here? Is this a single coherent change? I sort of feel like it is, because in order to use this test.sh, I need this environment variable to be set, and this is just kind of, maybe this is a separate change. Yeah, like this is not strictly necessary, is it? Like this is really the change. It's just that my motivation for putting the environment variable at the top level here was so that I could use it down inside the I could use it inside that earlier step. But I think this will work. Just trying to think whether there's anything I've missed here. No, I think this makes sense. So I'll say replace, let's just say use test script in CI workflow. And then I'll just separately say use env context. Let's say use WASM spec path instead of hard coding its value in CI workflow. Yeah. So if we ever need to change it, we'll only have to change it in one place. I mean, a lot of the stuff I'm doing here is not really necessary. Like I didn't even need an environment variable here. I could have just said it's a like ... spec, and then it just would have been a constraint of this whole setup that you have to clone these two repos as siblings and you have to give them a specific name. But I would just rather not bake that stuff in, so that you can see the difference between stuff that is actually essential and stuff that is just incidental. Anything that's just incidental, I think you should be able to, or in this case, you should have to like specify it at the time when you run it. You know, this script doesn't know where I've cloned that repo, and I would rather tell it where I've cloned that repo than have it be hard coded and then, you know, not have any choice about where that repo goes. Of course, I haven't actually run this workflow yet, so it's all getting a little bit speculative. Let's run it and check that nothing bad has happened. I mean, I haven't done anything particularly complicated there. There's no reason why it would break. Okay, great. I mean, the only thing I'm slightly nervous about there is that I can't see it actually running the... I can't... Is this just GitHub Actions being weird? Yeah, okay. That always throws me off. I'm like, where did the thing go? It's like, oh, I just didn't update the UI. Okay, so yeah, there it all is. That's exactly what I wanted to see. The only thing that was bothering me about this is that I've got the same situation here where it's I'm choosing what path to clone this thing into, and then I'm sort of hard coding that here. So I think what I'm going to do is set another environment variable here, which is wasmina path, and just say that's where I'm going to clone this thing, and then this can be that. And then now this explicitly is shell, so instead of saying wasmina here, I can put that in there. I'm slightly suspicious about the YAML situation there, though. GitHub workflows ci.yaml. The reason I'm suspicious is because it looks like a string literal, but then there's some more stuff after it, and I'm worried that that's going to upset the YAML parser. Yes, I think I was right to be worried about that. Line 20, column 7. Yes. Well, that is it's not happy about that. I think I can just make a sort of quoted block here. I want to look at the YAML spec, but it's a bit of a nightmare, isn't it? I don't even know what that's called in YAML. I would love to be able to show you. Oh, this is really block. Is it Blockstar? Is it this? Anyway, I'm sorry, this isn't helping. This is one of those specifications that I just don't know how to use. Maybe one day I should write a YAML parser so that I actually understand how to use this specification. But, you know, I need to answer a question about how HTTP works or something. I feel quite relaxed about going to the HTTP spec and just finding the answer. And increasingly with WebAssembly, I'm starting to feel that way. But with YAML is kind of the next level. Anyway, nonetheless, I'm hoping that now... Yes, okay. And yeah, this is what I wanted. It's just the value of the run key is that. So I think that that's what I want, is to be able to configure these two paths up here. Oh, the literal style. Okay, thanks, Tekken. Let's see if I can find it. Literal style. Oh. The literal style is denoted by the pipe indicator. It's the simplest, most restricted, and most readable scalar style. Yeah, I mean all of the sort of visual noise here is not helping, but I think you're right. Thank you, Tekken. This is what I was looking for. I was sort of dangerously close to it, but I would never have found that. Anyway, that completely justifies what I've done there. So let's say, what did I say? Use wasmina path instead of hard coding its value in CI workflow. So, I mean, that is coincidentally the same name as the environment variable that's set here. But I don't think that's a problem. You know, when the script runs, it's just going to overwrite the value of this environment variable with essentially the same directory. So I think this is all okay. I realize I'm making a bit of a meal of this, but I want to try and get it right if possible. Let's see this run. And if it runs, I think that's it. That was all I wanted to do. Now I can run the test locally, and the same set of the same test script is going to be running on CI as well. So that's kind of where I wanted to get to. All right, same problem with the GitHub Actions UI here, but this seems to be successfully running the correct file. So that is great. Okay, I'll check that off. this has been here for ages, so I think while I'm in here, I'm going to do the same thing here, which is just to... Basically what I want to do is stop putting Ruby version in here and store it in a .ruby version file instead. So I'm going to put 3.1 in a Ruby version file. I think I'm going to have to force this because Ruby version is in my git ignore. I'm hesitating slightly because I can't just remove this because this doesn't know, because I'm not cloning this repo into the root of the Actions workspace. It doesn't know where to look for my Ruby version file. So I think there's a way you can configure this. In fact, I know there is because I've used this action before on mono repos that have multiple projects in them. I just need to find out how to configure it. The working directory input can be set to resolve Ruby version, tool versions, and gem file lock if they are not the root of the repository. Well, that is exactly what I'm doing. So I need to set working directory to be the right thing. So I'm kind of exchanging one thing for another here. This needs to be working directory, and then it's just this again. So that's going to... So what I've done is I've moved the Ruby version into... I think that's a single, like, coherent commit, isn't it? Move Ruby version into Ruby version file. And the purpose of having this Ruby version file is firstly so that Ruby, it's just a convention that that in a Ruby project that you'll have whatever version of Ruby is required by this project in this file. The reason I had the Ruby version here in the first place is because I'm using Ruby 3.1 features like hash punning and possibly pattern matching that doesn't emit warnings. I can't remember if I'm actually using any of the pattern matching features that would emit warnings in 3.0, but definitely hash punning is something I'm using. So I need it to be this version of Ruby specifically. This is the latest version of Ruby. And I'm using Cheruby, which will look in this file to decide what version of Ruby to use. And also this GitHub action will use the Ruby version file, not needed with a Ruby version file. So it's kind of nice to just stick this in this file and let the action pick it up automatically. But in this case, I'm having to give it a little bit of a hint about where to look. I'm going to say what's it called? Ruby setup Ruby action needs to know where to find the Ruby version file because it's not in the work, because we're not cloning the repo in the workspace root. I think that's probably enough. Please work. So what we're hoping to see here is it installing Ruby 3.1. Check out, well, it's passed, so I must have done it. Here we go. Using 3.1 as input from file Ruby version. Great. Great. Okay. All right. I think that's all of my infrastructure chores dealt with. There's a bit more refactoring here, but I'm going to... Okay, I'll tell you what I'm going to do. I'm going to look at Ufuk's pull request, because I said I would, once I got to the point where... I mean, it's only the float literals. I don't know if that's the... when he's talking about spec compliance, I don't know if he's just talking about the literal syntax or if he's talking about some other thing that I've overlooked. But really, literal syntax is the only thing that I've implemented so far. So let's look at that and see if there's anything that that hasn't come up yet as part of making the test pass. I'm sort of tempted to plow on and try and get some more tests working, like rather than faff about with doing more refactoring. I've got something of a hunger for some more to make some more tests pass. So we investigated did we investigate float coercion impact? Well, yes, sort of. I mean, I've got this separate thing to actually understand it. All of the rest of this is just fiddling around and refactoring. So I think I'm going to press on. I'm going to look at the Fuchs PR briefly, and then I'm going to press on to tease where we're going next. I mean, there's a choice of places to go next. There's f32.wast, which is let's start implementing floating point operations. So this is essentially the analog of i32.wast, which was let's implement things like let's implement instructions like i32 add, i32 sub, i32 mul. So in f32, we're implementing operations like f32 add and sub and mul, which are probably fairly straightforward, but then we get on to things like ceiling and floor and truncate and nearest, which is gonna require at least a degree of sympathy with how the WebAssembly spec expects these things to behave. So I mean, if you saw earlier on this stream, several episodes ago, there was the drama with trying to get division and modulus working correctly with integers, because actually the way Ruby implements those things does not match the way that the WebAssembly spec says they should be implemented. And I fear that in these cases, there might not be agreement about what exactly nearest means or what exactly truncation or flooring or ceiling means. I mean, as those words are coming out of my mouth, I'm thinking, well, that shouldn't be the case. This should have the same meaning in Ruby, but I don't really know. In fact, it's only these operations, it looks like, although presumably there's some F64 stuff further down. Oh no, sorry, this is the F32 file. Okay, so there's not actually a huge... I was expecting to see like a larger number of operations than that. There aren't a very large number. So this is one option, is we could start looking at this. Oh, yeah, okay. It's actually broken out into several separate files. There's this F32, but there's also F32 bitwise. I don't know why these are broken out into separate tests, but these are for... What's this? Absolute negation... copy sign. I think this is copy the sign bit from one number to another. And then there's also all of the comparisons. I mean, maybe these are broken out into separate files just because they're so long. Like here, there's only 6 comparison instructions, but they're testing all sorts of... It looks like they're testing all of the different, edge cases and different combinations of things. So maybe it's broken out just for length purposes. So that's one option, is try and get all those working. But I was also tempted by, is it conversions? Yeah, because this file, it doesn't look like it's really doing any arithmetic on... So this has got conversions. Basically, this file is about converting between all of the formats of number that we've already implemented. So without getting into the details of doing arithmetic on them, this looked to me as though... So there's some stuff here that's about converting a 32-bit integer into a 64-bit integer, signed and unsigned. there's a thing here about converting a 64-bit integer into a 32-bit integer. I guess that's just by throwing away half of the bits. I'm not entirely sure. And then there's all there's similar things about, this says trunk. So this is about, I mean, this looks like it's turning a 32-bit float into a 32-bit integer. I'm not 100% sure. And then there's this sat, which I think is for saturating. So we've already seen this reinterpret thing. This is basically the identity on the encoded number that we're already using to represent floats. But this is going in the other direction. This is saying interpret. I'm actually not sure this is meaningful. This might still be the identity because we're representing both of these things the same. So actually it doesn't matter what direction the conversion goes in. But, in any case, this is sort of appealing to me because this doesn't actually involve any arithmetic. This is just about, or actually, I suppose the thing that I'm more interested in with this is that it's sort of a stress test of our representation. Like, are there any hidden problems in the way that we're representing floats and I suppose unsigned integers that will cause any of this to sort of go badly wrong? So I'm sort of, where I was going when I opened these files up was I was going to say, we should definitely do conversions first because it's simpler. I mean, actually, this f32.wast doesn't look too intimidating now that I see it, but actually any one of these could turn out, and especially because there are a large number of tests in this file, any one of these could turn out to have some annoying edge cases that we're not ready to deal with. Whereas I mean, there's quite a lot of tests in here as well, but I mean, maybe it's just my knowledge that some of these are the identity function, but it sort of just makes me feel, I feel a little bit less intimidated by this. Even though that this is a larger number of operations, but they're all, I would hope that these conversions, because we're already storing floats as unsigned integers, I would hope that these conversions would largely be a question of just composing operations that we've already implemented, and then there might be some places where we have to implement the inverse of operations that we've already implemented, where those operations are bijections. Anyway, that was a very long-winded way of saying I'm going to do this one next. I've got to be a little bit careful because I was going to add it to the test script, but I think I'm not going to do that. I think what I'm going to do is run it sort of manually like this. Because as I'm worried about adding this to what I don't want to do is break the build, right? So I'm worried about accidentally adding this to the conversions.wast to the test script and then accidentally like pushing it before I'm ready and then breaking the build on GitHub, which I realize is a victimless crime. But it would just annoy me if I did that. So I think at least for now, I'm going to start by running this. But I just have to make sure that I remember to also run those tests. Maybe what I'll do is say I'll do this and then wasm spec path equals spec test.sh. So what I'm doing here is, it's not really helpful to do that. It's not really helpful. Never mind. I'll just do this and then I'll just remember to run the test before I push. That's what my system is going to be. I'm going to run this thing that I know is failing. I mean, this is the point at which I'm thinking I really should just I should really just set up RSpec. Because this is exactly the purpose of having like a pending test. thus far I've sort of resisted plugging in even the most rudimentary of testing frameworks here, but as long as I don't screw anything up, this is going to be fine. Doing it this way is going to be fine. But that's just quite a big if, isn't it? Let's see how far I can get with my extremely bad testing setup. But it's not bad that I've managed to get through 5 streams before my brain has wasted a single moment thinking about what testing framework do I want to use. But now I'm hankering for something a little bit more sophisticated than Raise in my code. But plugging an aspect could be a whole rabbit hole in itself. So I'm going to continue to ignore that for now. Anyway, so what's happening here? So it turns out, oh yeah, I vaguely remember implementing these. Extend I32U, S and U. Oh yeah. This is a bit... I wish I hadn't used a regular expression here. Because I think that what I actually meant here was extend 8S or extend 16S or extend 32S. And then it was only, I think, the 32 that had this weird variant. Wasm spec path. Yeah. Yeah, I mean, given that I experienced regret just then when I saw that regular expression, I think I'm gonna make this change for now. List extend operations explicitly instead of using a regular expression. This makes it much clearer which operations I did run the specs. Why are you yelling at me, Tekken? I did run them. See? They pass. Okay. Right. What was I doing again? Right, okay. So I've already implemented extend I32S. I've already implemented wrap I64, apparently. And yeah, that's one of these things that is just the identity. As is this, apparently. Like, I've already got reinterpret F32, reinterpret F64. So I can see that I've already implemented some of these, but what I have not implemented is trunk F32S. So where is that? Here. So how many of... I'm confused about what's going on here. Okay, these are the things that actually run. Okay, so it's this. trunk I32 trunk F32S. So it's this one. Okay, well, I don't know what that does. That, of course, is what the specification is for, but let's just see where I would implement that, because there's a whole... This is the integer operation section here. Again, I think this is somewhat desperately in need of some refactoring so that I can more easily find the bits I want to. I mean, do we even have... I guess we don't have... I was going to say, like, oh, and there'll be a separate section for floats, but of course we haven't implemented anything apart from f32.const and f64.const, which necessarily have their own separate thing here because it involves not evaluating their argument, but parsing the string. So I guess this is the only section of operations that we have at this point, so I'll just stick it at the bottom of here. Trunk F32S. So I will look at the specification, but let's just see, like, this just calls i32.trunk F32S. So you pass in a 32-bit float and you get out a 32-bit int. Is this truncation in the sense that we're just taking the whole part of the float? Like, it seems to be. So 1.5 becomes 1. Minus 1.9 becomes minus 1. So it does... I can't see one that's got a positive... I sort of wanted to see what happens to 1.9, but I think it is just chopping off the... Yeah, I mean, essentially, I think it is doing what Ruby does. There is literally a method called truncate on float that says truncated towards 0. So that means you're always... Basically, you're throwing away the part of the number after the decimal point. So if it's minus 1.9, you're throwing away the 0.9 part and it's being truncated towards 0. If it's positive 1.9, you're throwing away the 0.9 and it's truncated towards 0. So I think we can probably just use Ruby here. So what does that look like? This value has already been... We've pre-evaluated it because everything in here has had its argument pre-baked. So we just need to... We need to turn it into a float, a Ruby float. So we need to do like integer to float value, like truncate. It's signed as well. Hold on. Let's have a look at the WebAssembly spec, because I'm not completely confident I understand where does the signed part come in? Is that saying that the integer that we're returning is... Hold on, let's just... I'm trying to talk and think at the same time here. Conversions, there we go. Okay, trunk F32S. Okay, so here's... Again... disregarding the fact that I'm not 100% sure that this is what this is mapping onto, but I think it must be. So this is trunk superscript S as opposed to superscript U. So this looks like this is the signed versus the unsigned version of truncation. These M and N are going to be the bit widths of the float and the integer respectively. So I don't know what to do if it's not a number or infinity. I don't know if the tests check that. I can't see. Oh, I guess there's assert trap here. Yeah, but I'm ignoring that for now. So let's ignore the sort of throw an exception behavior or undefined. If Z is a number and trunk Z is a value within range of the target type, then return that value else if the result is undefined. Right. Okay. So what is this trunk function? Truncation of rational values is written trunk plus or minus q with the usual mathematical definition. Trunk plus or minus q, again, I suppose q ranges over rational magnitudes. So this is like, I don't know why it's saying rational as distinct from floating point, but whatever. Yeah, am I missing something there? I don't think that's hugely significant, so let's just carry on. So this plus minus here means that if Q was positive, then I should be positive. If it was negative, then it should be negative. So this is kind of matching signs here. I is a natural number, and okay, right. Yeah, okay. So this is saying that, at least thinking about, yeah, that is what we thought. This is truncating towards 0. This is saying, at least thinking about the case where Q is a positive number. If Q is a positive rational number, so not a whole number, then I is the integer that is less than or equal to Q, but more than 1 less than it. So it's the integer that lies in the 1 unit wide section of the number line that is less than this number Q. So it's going to be truncate. If it's not already an integer, it's going to be truncating it towards 0. So that is what we thought it was. So that's what this function does. M and N. So M really doesn't matter. M is not. So M is the width of the float in this case, and N only matters because of the possible range of this number, which I think I'm just going to ignore, because that would mean raising an exception. Essentially, it'd be this. That's this assert trap behavior that I haven't thought about yet. So how's this different from the unsigned version? I mean, this looks like literally the same definition, except for this range check. So maybe for right now, the signed or unsignedness doesn't really matter. Okay, so, all right. Oh, except the fact that... Sorry, I'm being very slow here. The return... Okay, the return value of this needs to be... think about what's going on here. Firstly, I think this integer to float, I don't think I've got that. Yeah, I've got the other way around. Oh no, I don't have it the other way around either. What did I have that was doing that conversion then? Oh, I'm just doing it inline. Okay, well, fine. So it's, what a mess. There's all this pack and unpack format stuff. I'm gonna cobble this together, and then I think we need to do a refactoring because this is a right mess. But if this integer to float existed, it would turn this, value here, like all values, is just going to be an unsigned integer. This is going to turn it into a Ruby float, which might be a positive or negative number. Then when we truncate it, we're going to get a positive or negative integer back. And then that has to be translated into an unsigned. So I've got a helper that turns a signed number into an unsigned number. And so because the result of all of these things needs to be an unsigned number, then this needs to be, I can't return a negative number, which truncate might be. I have to do this to, so this truncation gives me like a signed result essentially. Yeah. So this is sorry, I was just sort of thinking, yeah, this is right. Or it would be if I define this method. So I take the unsigned integer that is the argument to this truncation function. I turn it into a Ruby float. I truncate it, which, praise be, does the same thing basically as what this spec function does for WebAssembly. And then I'm going to sort of, having got a signed integer in my hand, I'm now going to encode that as an unsigned integer. And then I think that's going to be the right answer. And then all I need to do is actually implement this. I mean, right now, the implementation of this is, I'm going to need to pack this and then unpack it. And I'm just going to need to use the right format. Now, in this case, I was going to say I know what the format is, but it depends. In this case, I know that it's I32. Yeah, okay, hold on. Let's do this. Raise unless bits equals 32. I just want to see something work here, and then I can finesse this. So if this is I32 trunc F32S, which might be the only way that you can, there might not be an I64 trunc F32S, in which case I don't need to worry about this, but let's just play it safe. So I need to pack this as a 32-bit, which I think is L, integer, and then I need to unpack it as a 32-bit float, which I think is F. Then truncate it. I mean, let's see what happens. I mean, that's my best guess at what this trunc F32S is supposed to do. Oh, it was quite a good guess because they all passed. Okay, great. All right. And then there's trunc F32U, which I guess is going to be broadly the same thing, but without the conversion to unsigned, because it should already be unsigned. But then unsigned doesn't do anything unless its argument is negative. So arguably I could just call that, but I think it's probably a bit messy. It's tempting to just add it in here, but I think it's a little bit unclear to do that. I think there's already one place where I'm using unsigned as a no-op, which is a little bit naughty. but I'm sure I had a good reason for doing it then. I'm not sure I have a good reason for doing it here. So I'll just add this for now. How did I used to, back in the day when I implemented, it used to look like this. Implement the trunk. Well, it's specifically I32 trunk F32S instruction. I think I'm gonna just acknowledge here. I've hard-coded the pack formats for 32-bit integers and floats, but we really need an, what is it in this case, integer to float function that encapsulates this detail. Because what I'm going to do next is just copy that to make trunk F32U. So this is going to be the same apart from this. I don't need to do the conversion. This is going to make it was this even right? Yes. Sorry, I was just confused that, oh, L is for unsigned integers, but of course value is an unsigned integer. It's the float that's signed. So what is this going to do about it? Well, I was just thinking, what happens if I do get a negative number here? And I think the answer is that's undefined behavior. It's part of this assert trap. So I think I can sort of ignore it for now, because as long as the input is within range, then this is enough. Yeah. Okay. I can see that the next thing is going to force my hand with respect to the pack and unpack format. So, let's just say F32U. Obviously, there's quite a lot of duplication going on there, but yeah, like I say, I think this next one, trunk F64S. So this feels like I can probably generalize. I can't, can I, because of the pack and unpack? Let's just duplicate this for now. So this is going to be 64S. And is this I32 trunk 64S? Yes. Okay, well, I'm not going to do anything clever for now then. The reason why I've got this constraint here is because the number of bits directly dictates what format I'm using here. So this needs to be we're still packing in is this right? We're still packing in a 32-bit integer. But what does it mean to... Okay, F64. I'm not sure I understand like what the difference is. Oh, right. Right. Yeah, I wasn't thinking straight. Okay, so what this means is that the float that we are being given is a 64-bit. Is a 64-bit value. So oh god. So I don't want to pack it as an L, I want to pack it as a Q, because that's a 64-bit integer. And then I'm unpacking that as a double, but then we're going to treat that as a 32-bit number, a 32-bit integer. I think that's right. That feels very odd. But, I mean, it makes sense that, like, although a double, a 64-bit float can be much larger than a 32-bit float, it's also just got more precision, so it's not completely nonsensical to think about taking a 64-bit float and truncating it to a 32-bit integer, because it may well be within the range of a 32-bit integer, which I'm not checking this here because I don't have a way of raising exceptions. Yeah, I think this all makes sense. I think this makes sense to me. Yeah, I think this is right. It feels weird, but I think it's right. Yes, it is. And so, well, let's 64S. And then we want 64U. So it's basically this one. But instead of L and F, it's Q and D. I'm a little bit unsure about the order I've put these in, but whatever. I've put the signed and the unsigned ones together, I suppose, rather than put the 32-bit and the 64-bit ones together. And it's like a 2x2 matrix. I've got to serialize it in one order or another. So again, I think that's going to be correct. Yes. All right. So the unhandled exception on line 169 is because this is now being called with 64. So it's I64 trunc F32S. Right. So now I have to make this work. But now that I'm thinking about it, it doesn't matter. I think that the only thing that bits matters for is the range checking and I mean here where we're using it to convert to unsigned. But actually it's the width of the float that determines the pack and unpack formats here. L and F, or Q and D, which I assume is the same as what I had down here. Yeah. So it's actually only the width of the float that matters, because the width of the integer, it only affects behavior that we haven't implemented yet. So hold on, I'm getting ahead of myself. Let's commit this. But the reason I was getting ahead of myself was because I was curious about this exception. So actually, I think I've now convinced myself that I can take all of these out and it's just going to do the right thing for all variations, because as long as I'm not having to do the range checking, I'm going to have to come back later and add that. But for right now, just trying to get the correct result on inputs whose output is defined, i.e. all of ones being tested by assert return, I don't think it matters whether a 32-bit or a 64-bit integer is being asked for, because I'm just going to give you whatever the integer is that you get as a result of truncating this flow, and it will be as wide as it is. And yeah, it's only the exception cases that we're not testing where that is going to give the wrong answer. You know, it's going to give a number that's wider than it should be, rather than just raising an exception, which is what the assertion is checking for. So I think I can just take all of those out. Yeah, see, that's fine. So I'm going to say remove raise, remove bits guards to support i64.trunc f star instructions. So I'm just going to write a line to explain that. I'm going to say the width of the resulting integer doesn't matter in the cases we're currently trying to make work, i.e. when the output is defined. When we start supporting assert trap, we'll need to use the integer width to check that the truncated flow is within the range of the resulting integer, but we're not doing that yet. So we can just ignore well, I'm just going to say so, but we're not doing that yet. I think that's enough information to understand what's going on here. All right. I'm conscious that I still haven't looked at Ufuk's pull request. I got distracted by, I started trying to give a sneak preview of which tests we were going to look at, and then I started looking at it. So at some point before the end of the stream, I'm going to go back and look at Ufuk's PR, because he took the time to put it together, and I want to take the time to actually, having kept myself in suspense about the content of that PR, Oh, okay, Tekken, thanks. All right. So maybe there's nothing earth-shattering in that PR, but nonetheless, I want to do in the courtesy of opening it and looking at it on stream because I've been averting my eyes so far so that it didn't, so that there were no spoilers. So I'm going to try to remember to do that before I wrap up. But for now, I'm going to try and keep this momentum up. Okay. Convert F32 dot convert I32S. All right. So this is a legit. This is going to be the first F instruction we have that's not just F32.const. So I'm going to need a little bit of infrastructure to support this because at the moment this whole conditional that we're inside is I32 or I64 dot. So I think I'm going to need to sort of duplicate this business here. Am I doing the right thing? Like, this is the problem when the file gets so long. But yes, I think I am doing the right thing. So this is like in whatever. And am I going to need a mask on the end of this? Haven't really thought about that. Haven't really thought about that. Anyway, what am I trying to do? So this is going to be... I mean, I'm doing this in anticipation of needing to support not only F32.convert I32S, but also F64, which indeed I am going to. So let's just save ourselves the pain and have this business. This all makes sense. I still want to slice out this number so that I have either F32 or F64. Bits will be 32 or 64. I assume that I want to do the thing where I'm pre-evaluating its argument, but we'll see if that is actually true. But for now, it's this. Convert I32S. Okay, so what does that mean? So again, numerics. I see something somewhere helpful. In fact, it was only because I've never clicked on this by mistake. This is actually quite useful because when you go through to numerics here, there's no local table of contents in this numerics, but actually if you click on the top level thing here, I mean, this is a game changer. I can actually navigate within one of these sections. Okay, so I was in the right place anyway, I think. Oh, this MathJax. It feels like it's getting slower every time. I don't know if my Mac is losing the will to render MathJax, but it seems like every time I load this page it takes longer. It's probably just a memory leak, it's fine. Okay, so convert. If I was convert, where would I be? Okay, again, convert S. All right. Okay, let's get our head straight. What the heck is this thing? Okay. So maybe this is always the best place to start, is to just try and imagine what we think this function is doing. F32.convert I32S. So this takes a 32-bit integer and it returns a 32-bit float. And it looks very much as though what it's doing is returning... This is like to float, basically. I give it this 32-bit integer and it gives me back, well, so this is a very similar number. It's actually one away. So you can see this is, I mean, this looks like this is the maximum. I think this is the maximum. Is that right? Oh, Ruby's not going to tell me because it only has 64-bit floats. But this looks like very large. So it looks like this is pushing up against the maximum magnitude, in which case it's... I can believe that this number is not representable as a float, and that actually we have to represent it as 8 on the end rather than 7 on the end. So I think intuitively, I think I understand what this is doing. It's just you give it an int, a 32-bit int, and it gives you the closest 32-bit float that it can. But what does that mean? Let J be the signed interpretation. Oh yeah, so this is the S. All right. So we have to, before anything else, let me just, I know I'm doing this a lot, but let's just say raise unless bits equals 32. Like I'm getting really paranoid about like doing something. I kind of liked that I had to, that this raise forced me to stop and think about whether it was okay for these to work with 64-bit ints in this case, which I've convinced myself it is okay. Whereas here I'm not quite so confident. Well, because the reason I'm not confident is that I haven't thought about it at all. So that's what the raise is for, so I don't have to think about it. So assuming that we're talking about a 32-bit float, then first, so the S is meaningful here because it's first we've been given a 32-bit unsigned integer because that is our internal representation of 32-bit integers. They're all unsigned. But we have to take the signed interpretation of it. So before I do anything, I have to take the 32-bit signed interpretation of the argument. That is a good start. And now it's saying return float sub n of that signed interpretation. So n being the width of the float, I guess, which is 32. You see, I've already screwed up because, well, here bits is the number of bits in the resulting float, but it's the 32 in the instruction here that tells me how wide the integer is. So in the same way as I had float bits up here, thanks SexFind Pro. Oh no, am I going to have to find a way to... Hold on, how do I... Okay. All right, I've dealt with the person / bot that was spamming the live chat. What I was saying was, in the same way as I've got float bits up here, and indeed I'm raising unless it matches, I think I want sort of the analog of that here. I want to say this is like integer bits is slice the 32 out. I mean, I don't really need to do that, but I've already written the code to do it. And then this is like, just for the sake of safety, let's make it so that for now, until I think about it, we're expecting these two things to be the same bit width. I don't know if that actually matters yet. So, but when we do the conversion from unsigned to signed, that is using the integer bit width. So, and that was still going to be the number 32, but this is like a different 32. So it's important that we get that right. Okay, so we've taken the signed interpretation of the integer and now return, in this case, the 32-bit float. And I think that this is just going to be... I'm expecting this function to just be like, what's the nearest float to this signed integer, basically. So what's this saying? A real number r is converted to a float. R is an exact floating point number, then return r. So this is the identity if the number that's been passed in is exactly representable. We need to clamp to positive and negative infinity. I don't know whether any of the tests are checking that. And then all of this looks like it's language around... I mean, I would describe all of this in summary as the closest float. Like, I think that's clearly what this function is doing. In fact, look, there's even a little... there's all these sort of edge cases for zeros and infinities and stuff. But then otherwise, it's defining this helper function called closest, which is just... This is using the magnitudes of differences between numbers to just say return the candidate that is the least far away, that minimizes the error, basically. So find the float that is closest to the number we passed in. Now, I'm pretty sure that that is what to f is going to do. Like if we look at... Because this is essentially what we're going to do is take an integer and we want to find the nearest float to it. Why is it gone to 2r? Did I click on the wrong thing? Am I losing my mind? 2f. Okay. Convert self to a float. Okay, well, very little detail about what that means, but I think it probably means the closest float. Now, the thing that stresses me out about this is that it's not going to give us the closest 32-bit float. It's going to give us the closest 64-bit float because Ruby doesn't have 32-bit floats. So I think that, well, like if I do this, then that's going to give me the nearest 64-bit float. But that's no good to me anyway, because we represent floats as integers. So I've got to convert this back to an integer anyway. So I've got to do this dance. I've got to do float pack something, unpack one something. And I suppose my best hope here is that if I pack this, even though it's a 64-bit float, if I pack it as a single precision float, as a 32-bit float, and then unpack it as a 32-bit integer, then inherently this is going to involve rounding it, right? Like, however precise this nearest, this is going to give us... The real question here is whether these two operations compose in the way that we want them to, right? Is finding the nearest 32-bit float to an integer the same mathematical function as the composition of finding the nearest 64-bit float to an integer and then turning that 64-bit float into a 32-bit float, however that works? Like, I'm not sure how that conversion works, because that's what I'm asking Pack to do here. I'm giving it a Ruby float, which is a double IEEE 754 double precision 64-bit float, and I'm asking it to pack it as a single precision 32-bit IEEE 754 float. And then, less relevantly, I'm asking it to then unpack that as a 32-bit integer, because that's what my internal representation is. But it's like, it's really a question of whether the semantics of this packing composes nicely with finding the closest 64-bit float to an integer to give you the same result as if you'd just gone directly to the nearest 32-bit float. I'm really just rambling because we should just run this and see if it works. But that's the thought process, is that we would like for this two-stage process of first find the nearest 64-bit float and then turn it into a 32-bit float to give us the right answer. And it's not, well, I was going to say it's not obvious to me that that's going to work. I mean, I really don't know what this operation is here. This pack a 64-bit float as a 32-bit value. I don't know what Ruby does there. My hope would be that that's like a well-defined operation within IEEE 754, and furthermore that it's been designed so that it composes with this sort of nearest float operation such that you can compose them in that way. But anyway, I'll just shut up. Let's see if it works. Yes, it worked for all those cases. So that's fine. I guess we'll just go with that. Okay. Now, having done that, I'm just wondering whether I need the raise. Again, the integer bits don't really matter here. What matters is it's the float bits that dictate this, that dictate these format strings. So actually, all that matters is that bits is 32, because that's what determines these format strings. I mean, really, I need to make all these format strings like, you know, these all need to be, I need to have a float to integer and an integer to float where I can just pass in the bit width and have this do the right thing sort of dynamically. But for now, I think I do need this raise to be here because the pack format is hard-coded. Yeah, there's no requirement for these. There's no reason why these two things need to be... There's no relationship between the integer bits and the float bits. The relationship is between the float bits and the pack format. So I don't care what the value of integer bits is. Okay. So I've implemented this thing. And it's specifically F32 convert I32S. And I'm going to say the integer bit width doesn't matter here, but the float bit width determines which format strings to use, and at the moment they're hard-coded. Okay, so trunc sat F32S. So we've already done trunc F32S, but now we're doing trunc sat F32S. Now, my expectation of what that is going to be, to me, what saturating means, so what sat means is saturating. And what that means to me is that I would expect this function to agree with the trunc F32S that we've already implemented, and for it to also be defined on more inputs, on inputs that are out of range, by like clamping to the maximum or the minimum possible value. Like that's what saturating means to me. But let's see what it says. Trunc sat. So which one are we doing? Trunc sat F32S. Okay, so it's this one, the signed one. If Z is not a number, then return 0. If Z is negative infinity, then return right. Okay. So these first three are like special cases for special floats. So like the saturating here to me means that you're trying to extend an existing function to give it, instead of it raising exceptions on weird inputs, you're kind of coming up with you're inventing outputs that are the closest thing to sensible. So like in this case, it's like if you pass in a not a number value, there's really no sensible conversion to an integer, but we're just going to return 0 in that case. And likewise, if the value is infinite, then we're just going to peg that to be either the largest or the smallest possible number, depending on whether it's a positive or negative infinity. So that's how we handle those sort of weird inputs. And then there's this sat function. So first we truncate the rational number, the floating point number, to get an integer, and then we do this sat signed at the bit width of the, which again I think is just going to be a clamp. I think this is like if you provide positive infinity, what you get is the largest possible signed number. I think probably if this resulting integer is larger than this largest possible signed number, I'm guessing that sat is just going to clamp it to the largest possible signed number. Saturation of integers is written, the arguments of these two functions range over arbitrary signed integers. Signed saturation clamps I to between the smallest and largest signed number of that bit width, and unsigned saturation clamps to I between 0 and the largest. So, 0 being the smallest unsigned integer and 2 to the n minus 1 being the largest. So that is all what I expected it to be. But it's just a little bit annoying because of these edge cases. Let's see. So zeros are fine. I mean, it'd be nice to see if we can get some of these passing. All of the funky edge cases like infinities and nans are actually at the end. So I think I might see if I can get this chunk passing, because these are all like just the normal case. This, return sat Sn of trunc Z. So these are all just like first truncate this float, which is an operation we've already got, and then saturate it. So like clamp it to within the, within the range. So what does that look like? Firstly, where do I implement this? Trunc sat F32S. I think I'm going to put it here because like it's a saturating version of this operation. Like just just because it's going to be very similar. In fact, arguably, I should sort of extract this because I'm going to need it. Okay, so let me think about this. Because this conversion to an unsigned integer is like the very last thing that we do. So we start out by saying but now we need to clamp it, and I think that there is. Where does it live? Is it just on number? Oh, comparable, yeah, that makes sense. So can just call clamp on it, which is quite convenient. So like result equals result.clamp. Min, max. The minimum and maximum are going to be with respect to the integer bits. So there's bits. So it is the 32. So the n here. So I think m is the bit width of the input we were given, and n is the bit width of the output. Yeah. Yeah, and like I said, it's with respect, the clamping is with respect to that. So I think here that it's bits. Like what I want to know is like what's the, when you look in the signed helper here, this size effectively, like this is the largest possible, the size over 2 is like the, well, it's actually 1 more than the maximum. If that's a distraction. Let me just try and put this together. So size is telling us how many numbers of this width are there. So if it was 8 bits, this is going to tell us that there are 256 numbers that are 8 bits wide, which is correct. But half of them are negative and the other half of them are positive. So the minimum is going to be half, but it's negative. And the maximum is going to be half, but it's 1 less than that. So again, if this was 256, we'd be saying that the numbers range from minus 128 to plus 127. Because like 0 is a positive number in this setup. So I think that's the basic shape of it. Let's see if any of them pass. Trunk set F32S. Yeah, okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9 of them passed. So that's something. I'm a bit surprised that we got an infinity so early, because I thought that wasn't going to happen until we got down here. Oh. So it was an error in truncate. Which one is that then? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I looking at the right thing here? Maybe not. Oh no, because of all of these other ones. What is wrong with me? I just missed all of those. Okay, so we are indeed at infinity now. So, all right. So my basic logic is sound for all of those. This can be like this. So like, I mean, I think that's fine for like the, should I commit that? Yeah, I think so. I'm going to say implement the, so again, this is I32, truncsat F32S for ordinary floats, I guess. This implementation doesn't yet support nan or infinity. I don't know what the right word for that is. I don't want to say normal because that means something else. Okay. So all right, so I have to deal with when it's infinite. I mean, it's sort of annoying because the reason I'm hesitating is because clamp, I think, will work fine. I think if I do float infinity clamp between 0 and 10, it knows what to do. And if likewise, if I clamp negative infinity, so like clamp is already doing a bunch of the work here. It's just that you can't truncate infinity. So maybe I can do something like result equals result dot truncate unless result infinite. Like, can I, basically apply that truncation conditionally? Ah, yes. Okay. So I think I can just say support infinity in the blah instruction. So I'll just say comparable clamp already knows how to deal with infinity. We just have to avoid truncating it first, because that doesn't work. Well, because you can't truncate infinity. Okay. So now it's just not a number that's causing the problem, right? Yes. Well, again, this is... Once I've got a float, yeah, I think what I need to do is say, like, if result is a nan... Okay, we're going to sort of recompute result here. We're going to say if result is not a number, then use 0. Else if result is infinite... Well, in fact, can I ask if it's finite? Yeah, I think that's slightly nicer. If the result is finite... No. Because these are the edge cases, right? I think. I'm just trying to work out if I like this more than, you know, just having a couple of you know, having another line like this, where you say, like, result equals 0 if result is nan. I think this probably makes it slightly clearer what's going on. You know, that there are two weird cases that we need to handle here, and then this is the reason why I was tempted to make this result finite, is because it's kind of nice to say, like, else result. Like, if you haven't detected some kind of thing that you need to do with it, then just return result as normal. But I think really this is by far the most common path, and both of these are just sort of edge cases. So yeah, I think that's okay. So now hopefully, all right, yeah, those all work now. So I think I just need to say support nan. Okay. How do I do for time? Oh, I don't know very long. But I think I'm nearly done. Oh, there's demote and promote. Oh. Poo. Okay, well, let's see how far I can get. It would be lovely to finish this conversions today, so I'm going to see if I can finish this. Okay, trunc sat F32U. What is that? Well, it's going to be a little bit like this probably, but also a little bit like this probably. So I think it's probably this, because... Oh, no, not just that, because the range is different. Now the range is going to be 0 through size -1, I think. Does that make sense? Yeah, I think in addition to not converting it's like, it's not just that the result doesn't need to be converted to unsigned. It also has to be clamped to a different range. So I think that I'm expecting this to just work. Yeah, it does. Okay. So that is actually all of them, because I've already done all of the thinking. So now what? Trunk sat F64S. Oh god. So what would this look like? Trunk sat. Oh crap. Yeah, it's like trunk F64S, but with saturating. So instead of L and F, it's Q and D, but otherwise all the same. Clearly a lot of tidying up needs to be done here. I was complaining earlier about, I've made a bit of a mess and I need to do some refactoring to clean this up, but all I've done so far is contribute to the mess. But I think that this is going to pass all of the trunk sat F64S tests. Yes. And now I just have to make trunk sat F64U work. So I'll copy 32U. Oops. But it's going to be 64U, and this is going to be Q, and this is going to be D. Ugh. This is really ripe for some cleaning up, isn't it? Okay. Oops. Okay. Come on. Let's just speed run this. Get it working. Convert I64S. Have I already got any instruction like that? Ah. Yes. This is the one I implemented earlier. Not so long ago. Look, if I just add it in here, because this already pulls out the... Hold on. This is F32. I was just thinking, like, is this raise going to be a problem? But I don't think it is. I think I can literally just say convert I64S. It's going to pick out 64 as the integer bits. This is not going to raise because it's a 32-bit float. It's going to interpret its argument as a 64-bit signed integer, convert that to a float, and then pack it into a 32-bit. Yeah, so I'm expecting those two will just pass. Well, I was wrong. But a lot of them passed. No, this is what I was worried about. That whole spiel I gave about whether those two operations compose, this is exactly what I was worried about. Because I don't think they necessarily do. Shit. was so close. So close to just working. Okay, what am I going to do about that? I mean, I suppose I should confirm that the problem is what I think it is. But that really doesn't fill me with confidence. The fact that it's one off, like, that was the one thing that we didn't want to happen. Well, I think I'm going to commit that because it's clearly passing some of the tests. So how well are we doing on this? One, two, three, 4, 5, 6, 7, 8, 9, 10. It's doing 10 of them. See, this whole section is test rounding directions, which is exactly the thing that I was worried about. Test rounding directions. So we managed to pass 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's these ones, or at least this one, that's problematic. Not sure what to do about that. I mean, what it... the reason why this is causing my brain to grind to a halt is that I can't immediately think of a way of fixing this that doesn't involve implementing IEEE 754, because I just don't think that Ruby exposes this function. I don't think that Ruby gives us... I don't think it exposes the find the 32-bit float that is the closest float to an integer. I don't think that operation is exposed by Ruby. It only gives you the 64-bit version of it. So I think to do this accurately, we need to implement it ourselves, which means essentially what that means is it's basically the same problem as parsing a float. It's the same problem as, like, here's here's the scientific notation of a floating point number that I want to express. Here's the significand, here's the exponent. Please give me a pattern of 32 or 64 bits that best represents that number. Like that is that function. That is, here's a string I've written down that explains either in decimal notation or in hexadecimal notation a floating point number that I would like to have a representation of. And then you get those 32 or those 64 bits back, and inherently what that is doing is giving you the closest expressible float to the rational number that you asked for. So it's not an unusual operation to do. But unfortunately, I just don't think that Ruby exposes it. Unless there's something I'm forgetting or missing. So it seems quite likely to me I'm going through the 7 stages of grief here. It seems quite likely to me that I'm going to have to implement that. And it's not... I do know how to implement it. It's not too bad. But it's a bit of a pain to have to do that. I just can't see any way around it. I think I'm going to have to implement it. So what situation am I in here? So all of these tests are still passing. Yes, because we're not even trying to run this conversions yet. This is so close. But you can see that it's deliberately designed to be right on the edge. Okay, so what do I want to do with my time? I'm obviously not going to get this. I'm not going to implement IEEE 754 by midnight, which is notionally when I would like to stop. Yeah, so I'm not going to get this file done, unfortunately. I will walk myself through how the conversion works to convince myself that I know how to do it. And then I'll think about implementing it. I mean, the reason I'm hesitating is because there's also a big old chunk of refactoring that needs to be done here, because there's a huge amount of duplication. I need a, float to integer and integer to float functions that know about these cryptic pack strings, so they're not scattered everywhere. There's also a lot of duplication here where, like, a lot of these saturating functions are the same. It's just that some of them are signed and some of them are unsigned. So I can see there's a lot of... I can safely remove a lot of duplication from all of this code that I've just generated here. But I think maybe it's a better use of my time to convince myself that what I just said, i.e. that I do know how to implement the conversion, is in fact true. So let's... All right. How long have I got? Well, 10 minutes. I don't have to stop at midnight, but, that's just when I start getting a bit tired. let's take, I want a floating point number to work with. So let's take this, 3.141596. I mean, this is perhaps quite a good one because I think this is probably, I don't think I can express it to that precision as a 32-bit, as a single precision float. So let's, encoding a single precision IEEE 754 float. So input is 3.141596. So that's in sort of float notation. That is this E, well, times 10 to the power of 0. And I suppose the main intuition here is that that is the same as this So yeah, 3.14. So that's this times 10 to the power of 0. But that's also, if we move the decimal point like 1 to the right, then that's now that times 10 to the power of -1. And we can keep moving the decimal point further to the right. So now that's times 10 to the power of -2, -3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'll do this in Ruby notation because then I'll be able to just copy and paste it. Right. So by rewriting this in this way, I've now already sort of got rid of the... Now I've just expressed it with some whole numbers. I've said I've got a significand here that is just a large integer. And then I've got an exponent here, which is 10 to the power of some other integer, which happens to be negative. But now I've sort of got a way of expressing this. I mean, I guess the other way of looking at this, and this is ultimately what I want to do, and it's what Ruby has done, is that is the same as this divided by 10 to the 15, right? So I've now got a rational number. I mean, this is not very mind-blowing because that's what 3.14 blah actually means. But like to encode this as an IEEE 754 float, I can't really do anything with this decimal floating point number because an IEEE 754, at least the binary IEEE 754 float, is in base 2. So having this as a base 10 decimal is not helpful. So my goal is to kind of try and re-express this as a base 2 decimal, and the first step is to kind of get rid of its base 10 decimaliness, which I've now done sort of by just expressing it as a ratio between two integers, right? The numerator is this huge number and the denominator is 10 to the power of 15. So going back to the format of a single precision float format, it's a sign bit and then 8 exponent bits, and then what is it, 23 Yes. What I've called fraction bits. So this fraction is, and you know, the significand is 1 dot fraction. So this is going to be essentially a 24-bit binary number, you know, with a decimal point in it. But we can sort of play a similar game here and sort of say, instead of being one dot all of those x's, we could just as well think of it as being 1 followed by all of those x's, right? So this is still a 24-bit binary number. And we could just adjust the exponent here to say, like, well, we found, instead of saying we've found a, well, this is what we want to end up with, is this sort of binary fraction that multiplied by 2 to the power of something is equal to the number that we want. This is an easier thing to find, really, is to find a 24-bit binary number that is equal to, or as close as possible to, this number that we're trying to represent here. And then we can always adjust the exponent here, because this is 2 to the power of something, so we can dial the exponent up and down to like move that decimal point around. So like once we found this 24-bit number, then we'll be fine. However, okay, so what does a 24-bit binary number look like? So if we shift 1 to the left 24 places, then we actually get a 25-bit binary number. So this here is 1 larger than a 24-bit binary number. So a 24-bit binary number is less than this. And I think the smallest 24-bit binary number is this one. So in as much as, if it was any smaller than this, then you could express it in fewer than 24 bits, which is totally fine. But what we're trying to achieve here is to use all 24 of these bits, right? Like if we've got this much wiggle room to express a number, then we want to fill it all up. What we don't want is to just say, well, we're going to have loads of zeros and we're only going to use the last couple of bits. Like, and it's complicated a little by the fact that the first bit has to be a 1, but like even in principle, if we've got 24 bits to express a number with, we want to use all of them, right? So what we want to try and do is try and find a number that is at least this. So let's say like min is 1. Yeah, so like, min is 1 shifted left 23 times, which is equal to that. And max is 1 shifted left 24 times minus 1, which is this number. No. This number, except with a 5 on the end. So I'm not explaining this very well, but what we want is to try and find a number between these two that approximates this number that we're trying to express, I mean, what would be great would be if when we did this division, we got a number that was in between these two numbers, but we know that we're not going to. We're gonna, if we do this division, we're gonna get, or at least the integer part of this is just going to be 3. So what we can do is, well, in this case, we need to scale it up. We need to say, well, this division here gives us the number 3, which is not within the range that we were looking for here. So let me set this. But again, we know that if we can find a 24-bit binary number, then we can also adjust the exponent, what it's multiplied by 2 to the power of. That is something that's within our control here. So the fact that this number is way too small is not a huge problem, because we could double it and then double it again and then double it again and keep doubling it until it gets large enough that we end up with when we like do an integer division here, we get a number that is actually in this range that does give us a 24-bit number. And then the only problem is that it's some number of powers of 2 too large, but then we can compensate for that when we set the exponent of the float. So let's say, does min to max include this? It does not. What about if we multiply the numerator here by 2 to the power of 1? It does not. Well, it's rather hard to guess what the right... I'm just going to try a few different powers of 2 here. Let's try 10. That's clearly still too small. 20. Is that in the ballpark? It's still a little bit too small. So that's about 3 million. The minimum we had here was about 8 million. And the maximum here is about 16 million. So 3 million is getting pretty close. In fact, I think if we bump this up to 21 and then go back to this, it's still too small, isn't it? Because it's 6 million now. Oh. Okay, so 22. Right. Now that is I can see that's between 8 and 16 million. This is 13 million. So if I go here, right. So now we found, given that this is the ratio that we want to express as a float, but at the moment, like the integer result of this division is just 3, which is way too small to be a 24-bit binary number. We found that if we multiply it by 2 to the power of 22, then we do get, let's see this, a 24-bit binary number. So let's say, so this is really scaling up into range. So that is equal to that, and as binary, that is that. Okay, so we've got a 24-bit binary number. So we have a 24-bit binary number, but it's 2 to the power of 22 too large. However, we're not going to write it down as a straightforward 24-bit binary number. It's actually going to be whatever we encode it as here is going to represent this fraction. It's going to have a decimal point after the first one. So it's actually, you know, but these bits will actually represent this binary number, which is, how much smaller is it? 2 to the, so it's a 24-bit number, so it's 2 to the 23 times smaller. So this actually comes very close to cancelling out. So I think what I'm saying is, so the resulting significand needs to be multiplied by, I think, 2 to the power of 23 minus 22 equals 2 to the power of 1. So this is maybe not particularly clear, but what I'm saying is there are two things sort of acting in opposition here, and I guess because of the magnitude of the number that I chose, they're almost cancelling out. That, like, when we write this as a binary fraction, 1 dot blah, that number is 2 to the power of 23 times smaller than the number we actually wanted to express. And yet the number we wanted to express was actually 2 to the power of 22 times too large. So yeah, that makes sense. So we wanted to scale it down by 2 to the power of 22 to get it to the right size, but it's actually already been scaled down by 2 to the power of 23 by what the encoding means, which is 1 power of 2 too much. So the final thing we're going to multiply it by is 2 to the power of 1. So we're saying, so we want to represent pi as this whole thing, well, I guess this, times 2 to the power of 1. And this is exactly what we need to fill in the blanks, right? So let's go back to this template. And we can start filling these in. It's a positive number, so the sign bit should be 0. The fraction is just the bit after the decimal point in the significand. So I'm not doing a very good job of selecting this. Oh, come on. So the fraction is that number. And then, this is a detail that I've been avoiding talking about for ages. The exponent is not just, you know, what would be great, this is an 8-bit exponent. I want it to be 2 to the power of 1. It would be great if this was just 1. Like, I would really like that. But that's not how the exponent is encoded. The exponent, so IEEE 754 exponent has a bias added. And so what that means is sort of an alternative to using, because we want the exponent to be signed, right? There's 8 bits of it. We want it to range from, not from 0 to 120 to 255. We want it to range from about minus 127 to about plus 127, so that you can, like, get positive and negative exponents. And the temptation would be to express that, to use, you know, 2's complement, which is what you'd usually use for a binary number, or indeed just have a sign bit, like, for the exponent. But I mean, this is quite clever, really. Like, it's the design of IEEE 754 is such that instead of using one of those encoding schemes, they just add essentially, well, in this case, because it's an 8-bit number, you sort of add, I think, 127. I think I'm right in saying that. Yeah, it's like the bias is all of the bits set to 1 apart from the top bit. So if you want to express the exponent 0, you don't, it's not all zeros, it's all ones, except for the top bit. And then, well, I mean, I guess I'm giving away what the encoding of our exponent is, because you're just adding 127. So the positive exponents are actually encoded as 127 up to 255, and the negative exponents are encoded as 126 all the way down to 0. And the reason for that is actually quite interesting, I think. It's, or at least I believe this is the reason, is that if you were to use some other scheme than that, then you would need to have some special dedicated logic or hardware for comparing the magnitudes of floats, because the exponent is obviously a major contributor to how large the number is, and it matters a lot whether the exponent is positive or negative when you're doing that comparison. So if it was 2's complement or something, you need to have some sort of custom, in the limit, you'd need to have some custom hardware that was able to sort of have some kind of conditional branch, or, decode the 2's complement representation of the exponent in order to be able to correctly compare, because numbers that have a negative exponent are extremely small and numbers that have a positive exponent are extremely large. So you have to be able to correctly compare those. And there's also there's a sign bit as well, so it gets more complicated. But the cool thing about just biasing the exponent, just adding like half of the range of the exponent, is that, well, ignoring the sign bit for the moment of the whole number, if you're just talking about positive floats, then if you want to compare them or sort them or whatever, you don't need any special hardware. You can just use the existing hardware, the existing logic you have for comparing integers, because the exponent is in the sort of top, in the more significant bits than the fraction. If 2 exponents are equal, then you just sort according to the bits in the fraction, which is what sorting those numbers as integers would do anyway. And if the exponent differs, then because of this biasing thing, you're actually because you're mapping a set of negative and positive numbers onto just a larger set of all positive numbers, they are in the correct order. So you can just sort them as normal integers. So I feel like that wasn't a very good explanation. Let me show you why that's clever. So if I do 10 times map random.rand numbers in the range, well, let's say numbers in the range 0 to 1. That's not going to give me very interesting. Let's multiply that by 10 to the power of numbers in the range of minus 100 to 100. And I've intentionally chosen all positive. The floats are all positive. The exponents are positive and negative here, right? So here's a load of numbers, and each of these is represented as, well, in this case, a 64-bit bit field, right? You can think of it as a 64-bit integer. That is the IEEE 754 encoding of each of these flows. And the point I'm making is that because of this exponent biasing decision, the design decision, it means that if you take each of these and, well, in Ruby, I'm going to ask Ruby to expose its underlying representation as a 64-bit integer. But of course, at the machine level, they're already expressed like this. So if I take this and I say I want to pack this, it's a double, and then unpack it as a 64-bit integer, then there are all of the 64-bit integer representations of those 10 numbers. And the point that I'm making is that if you sort those integers, so if I didn't have a special function for sorting floats, if all I can do, if all my hardware can do is compare two integers, then I've already got everything I need to compare two of these things or to sort them into, I mean, the sort is done by just comparing them, pairwise or whatever. So now I've got them like in order, and because of the exponent encoding sort of keeping all of those exponents in numerical order by bumping them up into a positive range, so that what used to be negative exponents are now just small positive exponents, and what used to be positive exponents are now larger than any negative exponent, positive number. This has now sorted them into the correct order, even though all I've done is sort the integers. I haven't compared two floats at any point here. I've just compared integers that are the encoding of those floats as a bit pattern. So if I now undo this, if I unpack, oh, no, it's not that. Pack this back into a string and then unpack it as a double, then what I'm hoping we'll see is that these are in the correct order. You can see it starts with an extremely small number that's times 10 to the power of minus 96. And then we get, oh, this is actually quite fortuitous. I've got 2 times 10 to the power of minus 14, and then 5 times 10 to the power of minus 14, and then a sort of quite small number here, and then a quite large one. So these don't even have scientific notation because they're sort of, the exponent is small enough that Ruby is willing to show us those directly, and then we get on to increasingly large numbers. So maybe this wasn't interesting enough to talk about, but I do think it's a cool design decision, right? The reason why this exponent biasing is done in this way is so that this works. And then the only complication is that if instead I'd made this numbers from -1 to 1, so now I've got not only negative exponents, but also negative numbers, that screws things up a little bit because the sign bit is set to 1 for negative numbers. So those actually get sorted second. First you sort all the positive numbers in the correct order, and then you sort all of the negative numbers sort of in the opposite order than they should be in, because they're being sorted as if they were positive. So they're going to be in magnitude order, not in the order they would appear on the number line, because they're negative. But if I do the same operation here, yes, if I pack them and then sort them and then unpack them. So again, I'm not sorting the floats, I'm sorting the bit encodings of those floats using integer comparisons. You'll see, yeah, like I said, we get, in these numbers, there were actually only 4 positive numbers and 6 negatives. So you can see the positive numbers are in the correct order, but then they're followed by all of the negative numbers in the wrong order or in the opposite order than they should be in. So here we get, what's happening here? God, I find this hard to read. Yes, these are in the opposite order than they should be in, because this is very close to 0, because it's times 10 to the minus. I've actually got kind of unlucky with these. I think these particular random numbers are a little bit confusing. Yeah, that looks like a slightly more diverse collection of. Yeah, okay, I like that a bit better. This makes it more obvious that these are not in the order that you would want them to be in. So this is very close to 0. This is very far away from 0, but in the negative direction down the number line. So it's a little bit more complicated in that if you want to sort positive and negative floats, all of the exponent stuff is taken care of because of the biasing design. But in order to get what you really want, which is them actually sorted, you have to do some post-processing. So I think if I partition them into positive and negative numbers, then you can see that like all of the negatives are there, but the wrong way around, and then here are all the positives. So all I have to do is say something like, I suppose I can do then negatives and positives. So if I do reverse the negatives and then add on the positives, then now you've got so we still, the sort has only operated on integers. It's just that you've had to do a little bit of post-processing to deal with the fact that the negative numbers have kind of come out in the wrong place in the list, but they're easy enough to find. And then once you found them, you can massage them into the correct format like that. So there's a bit of a digression, but I just think that's probably the coolest thing about IEEE 754 is that little design decision has kind of enabled a much more efficient way of comparing floats. And if they hadn't represented exponents in that way, then we wouldn't have the ability to do that. Anyway, the whole reason I'm talking about this in the first place is because we need to encode this exponent, this 2 to the power of 1. And instead of it just being all zeros with a 1 on the end, we have to add that 1 to the bias, which is all of these ones, 127. And so what we get, that 1 kind of causes all of these to overflow, and we get a 1 in the top position, and then we get 7 zeros. So I think this is, bias for single precision is, so our final number is 1, 2, 3, 4, 5, 6, 7. So I think that's it. 0 sign bit. There's our exponent with 1 added to the bias to give us, that's actually 128. And then there is the trailing 23 bits of our 24-bit number, because there's a implied 1 dot in front of, the reason why we came up with a 24-bit number is that sort of essentially guarantees that the first bit is going to be a 1, and then that first bit is implicit in the encoding. So these are just the numbers that appear after the 1 dot. So let me turn that into an integer. Right. So now the question is, if I take that and I pack it into a string with so that's a 32-bit number. So that's L for long. Right. And then I unpack that as a 32-bit float, which is F. Then I'm really, really hoping, after however long that took, that we get pi. Yes, we do. So, how close is that? Right, so I guess, well, I mean, this isn't necessarily indicative of the problem, but as you can see, the number that we ended up with here as a 32-bit float is not as accurate as the 64-bit float that comes with Ruby. I mean, that's not surprising. The problem is that I expect if I ask it to pack mathpy as a single precision float and then unpack it as single precision. Oh, I actually do get a different number. So what would this be as a long? Right, so that is actually slightly different. I mean, I'm realizing now that I didn't think about the remainder of this division, which is actually quite important. Because this division that I did here gave me a quotient, gave me the integer result of the division, but I didn't look at what the remainder was. Because if this remainder is more than half of the denominator here, then I should have rounded up. So maybe I've made a mistake there. So is this less than 10 to the power of 15 divided by 2? No, it's greater than. So I actually left out a detail here. So let's say, but the remainder is blah. Oops, it's this. Which is larger than half of 10 to the 15. So we need to round up so that we're picking the nearest integer. So actually, I should have chosen this binary number. So that should have a 1 on the end. 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 And this should be 1. And that is actually exactly what we got when we asked Ruby to pack pi as a 32-bit float and then unpack it as a 32-bit integer. So I slightly messed up there in that I forgot about the remainder. But that's an example of like why rounding is important, right? You've got to pay attention to like, it's not just doing the division here. You have to think about whether you're rounding up or rounding down. And in the case where it's exactly half, which of course can happen, that you end up finding a number that is exactly halfway between two different representations, then you have to have some kind of tie break. I think the default in IEEE 754 is that you round to even. So, of the two options you can choose, you pick the one that's even. I think that's right. That didn't happen here. It's obviously quite rare that you fall exactly halfway through the denominator there. So this doesn't illustrate the problem we're having, because it turns out that pi is not one of these numbers that doesn't survive the conversion by pack into a 32-bit float. Like, this didn't introduce any error in this case. It gave us exactly the same answer as we got by doing it ourselves. However, I mean, really, instead of choosing pi, I should have chosen the problematic number here, shouldn't I? Maybe that's something to do by hand, but hopefully what this does illustrate, I know this has been a little bit laborious to go through this, but hopefully it illustrates that it's not too complicated to do this. I mean, if you've never done any of this before, it probably seems a little bit daunting, but I think for me to write this down as a few lines of code is not a huge deal. It's just, multiplying stuff and dividing stuff and finding the remainder of stuff and, you know, adding a bias to a thing. Like it's just a series of arithmetic operations. So I feel pretty confident that I can implement this. And if I do implement this, then we won't be relying on this packing, you know, taking a 64-bit number and packing it as a taking a 64-bit float and packing it as a 32-bit float, and just sort of letting the chips fall where they may. We can completely control what this process looks like of approximating the original number, which again, because we've got it notated as a string, we know exactly what, you know, what the significand is and what the exponent is. So we can write it, each of these float notations can be written down as a ratio of integers like this. And then once you've got it as a ratio of integers, you can just step through, or now I want to turn it into a 24-bit binary number or a 53-bit binary number. And then I've had to scale it up. You know, I've had to double it 22 times to get it into range, and now I need to remove that. I need to subtract that from the exponent to make it balance out. So we can do all of that ourselves, and hopefully that will give us the right answer. So I didn't quite get to where I wanted to get to, which was to have all of these tests passing. But I have at least convinced myself that, well, firstly, I was right, that I do vaguely know how to do this conversion. I do remember how to encode a float. And I think all of this stuff, now that I've written it out and thought about it and reminded myself about how the rounding works and stuff, it has made me more confident that I could just write this down as Ruby code. So I think that's what I'm going to do next time, at least experimentally. Try just writing this down as Ruby and see whether it makes this problem go away, right? Because right now, I don't think Ruby is going to let me get any traction on this conversion not being what I want, because it's the only... Again, unless there's something I don't know about, I think the only language feature that it exposes that even gets close to being able to ask this kind of question is that pack-unpack interface. And it just doesn't give you any control over what happens under the hood when you call pack and unpack, which is mostly not a problem, except, you know, these tests have been deliberately designed to provoke edge cases of rounding and stuff. And so what Ruby's doing is not right. So this is like a much more insidious version of like, oh, integer division doesn't work the same in Ruby, because with integer division, we were able to fix it by just adding 1 to the result or something. Whereas in this case, I can't see an alternative to just working through this. So that's what I'll do next time, is just work through this, try it out, see if it gets us past these failing tests. I mean, that will then raise the question of whether we want to do any packing and unpacking. Like, if I've implemented this, the only thing I'm using pack and unpack for is essentially this. And so if I've implemented this myself, then I won't even need all of this pack and unpack business. I'll just have my own method that I can call and say, turn this significand and exponent, express that as... Oh, shut up, Siri. Express that as a 32-bit or as a 64-bit float. So maybe it's good that I didn't go through and deal with all this format string nonsense, because that might go away if I can implement this. But given that it is gone midnight, I think that I'm going to call it a night for now. I will push this I said I was going to look at a Fux pull request, so I shall do that. So this PR fixes some general spec compliance problems with respect to floats in the existing code. Strangely, these have not come up yet in any of the tests, but the existing code would fail to parse floats like capital A, capital P, capital E.